This is Artemis Launch Control. The engineering team is updating the NASA test director about the situation with the hydrogen leak. We should have an update shortly. This is Artemis Launch Control. The launch team has, the launch team has presented a recommendation of no-go for launch to the NASA test director and launch director. We are currently waiting a decision by Launch Director Charlie Blackwell Thompson. Stand by for that. Once again, the launch team has recommended a no-go condition for launch today to Launch Director Charlie Blackwell Thompson. She is conferring with Mike Seraphin from the mission management team, expecting a decision shortly. This is Artemis Launch Control. Launch Director Charlie Blackwell Thompson addressing her team just a few minutes ago. Says she has received their no-go recommendation but wants to hold off. Some additional thoughts and conversations are being developed about the situation and where the rocket stands, and said she will revisit it momentarily. Currently, we're in acceptable condition to hold. The launch team has the liquid oxygen in a stop flow configuration, safe at this time, and just awaiting a final a decision from the launch director at this time. This is Artemis Launch Control. This is Artemis Launch Control. Launch Director Charlie Blackwell Thompson just called a scrub for the launch attempt today, the second launch attempt. Again, Launch Director Charlie Blackwell Thompson calling a scrub for the day here at the Kennedy Space Center Launch Complex 39B. The team now going into the cutoff procedure after being unable to resolve a hydrogen leak. The vehicle is safe. NASA Test Director Jeff Spaulding now putting the team into a configuration to drain the propellants from the tank. Liquid oxygen reached a 100% state, and so the priority will be given to draining that tank. And currently they are underway. Again, we have a scrub for the day, a cutoff of the launch attempt of Artemis 1. We're working on a post-scrub interview, so please stand by for that. This is Artemis Launch Control. This is Artemis Launch Control. Again, the launch attempt, the second launch attempt of the Space Launch System and Orion spacecraft has been scrubbed. Launch Director Charlie Blackwell Thompson making the decision a little less than 10 minutes ago. Her team is now working to detank the rocket. Liquid oxygen reached 100% filled. Core stage only made it to roughly 11% before a hydrogen leak was detected. That leak detected at 7:15 a.m. Eastern Time. The team is focused and working diligently on the drain conditions. Since there was a leak in this line, the supply line, it is also the drain line. And so launch team taking care to make sure that they work that procedure, taking that into consideration, I should say. This is Artemis Launch Control. This is Artemis Launch Control. The launch director waved off today's attempt at launching at approximately 11:17 a.m. Eastern Time. The launch team ran into a liquid hydrogen leak while loading propellant into the core stage of the Space Launch System rocket. There were multiple troubleshooting efforts that were made to try to get the leak to stop and reseal the connection from the quick disconnect of the liquid hydrogen line. This is where the liquid hydrogen is fed into the rocket. Unfortunately, those attempts to troubleshoot it did not succeed. Engineers are still continuing to gather data, but also deconfiguring the rocket and detanking at this moment the liquid oxygen tank. It's currently down to 90% filled. Due to the aft strut constraint, they're going to drain that tank first, while the core stage liquid hydrogen tank is held at its current level of 11%. The aft strut constraint requires the team to have at least 50% filled liquid oxygen to over 5% liquid hydrogen. This is Artemis Launch Control. IFB check. Lauren, can we get an IFB check? Fire 2. Lauren?
Yep, I can hear you. Check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Check 1, 2, 3, 4, 5. Thanks. Check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Did you hear that, Joe? If you can stay close to the box, it'd be awesome. that light that they're reflecting at. So,
Welcome back. I'm with NASA Administrator Bill Nelson following the scrubbed attempt of the second launch attempt of the Artemis 1 mission, the Space Launch System and Orion spacecraft. Good to have you back, Administrator. Unfortunately, not the result we were looking for today either. Want to get your thoughts and your reaction.
We'll go when it's ready. We don't go until then, and especially now on a test flight, because we're going to stress this and test it and test that heat shield and make sure it's right before we put 4 humans up on the top of it. So this is part of the space business. I've told you before, you know, it's something I'm accustomed to. On my flight, which was Hoot Gibson and Charlie Bolden's flight way back, we scrubbed 4 times. Mm-hmm. We were delayed over the better part of a month, but the 5th try was an almost flawless 6-day mission. So this is part of our space program. Be ready for the scrubs.
Space is hard indeed. The question now on everybody's mind is going to be, when will we have another launch attempt? Any thoughts on that?
Well, the mission management team is meeting this afternoon. They're going to look at it. They're going to see, is there still a possibility now, or are they going to have to roll back into the vehicle assembly building? If they decide that's the case, then it'll be an October launch. And October, I would say, although the window opens in early, I suspect it'll be more like the middle. Because remember, the first week of October, we've got another crew. Mm-hmm. It's an international crew, 2 international participants on the crew of 4 that are going to the International Space Station.
That's right. SpaceX's Crew 5, NASA and SpaceX's Crew 5 mission scheduled for early October. You mentioned the MMT, of course, the mission management team. They're going to meet this afternoon, and then hopefully we'll have a press conference after that. I've been watching this launch team for the past 2 weeks now, and just impressed at how focused and how hard they work. Any thoughts you want to share with them about the effort they put in so far?
I'm very proud of the launch team. They do it right. They do it by the book. They do it very professionally. And that's why we have had this extraordinary success that we've had over the years. Sometimes we make mistakes, but we try to minimize those because these are human being lives on the top of that rocket. And I can tell you, when you strap into that rocket, you are very grateful that you've got a launch team like this that knows what they're doing, and they're not going to let you go until it's time.
And you know firsthand the power of those RS-25s and those 2 solid rocket boosters from your flight. Really quickly, before we let you go, you were over there at our VIP area as well. Had some special guests. You were telling me an interesting story about a guest you had there.
There was a young man before he was 7 years old. He wanted very much to be an astronomer. And he signed a document with other children that is on Artemis. And the reason that's so important, that young man named Gaskin died from brain cancer. His family is a special guest of NASA here today. Today he would have been 13 years old. And so we particularly recognize the family in front of all of our international and American guests today.
What an honor for that family to have them there. All right, that'll do it for us. Thank you, Administrator Bill Nelson. Appreciate you being here. Unfortunately, we didn't get a launch today, but the hope is we're going to keep staying with it and see what happens next. That's going to wrap up our launch coverage on NASA TV and our social media channels. For more updates, tune in to our social media accounts. You'll be sure to find the latest on the Artemis 1 mission there. For now, have a good day. We'll see you next time.
Locked and we have good to send that command. We have 31 minutes and 32 seconds for our support. Go for status buffer dump.
Since the retirement of the space shuttle, the engineering team is absolutely critical for Hubble. It always has been.
Without the shuttle going up to replace any equipment failures that we have to make do with what we have. What we really are concentrating on is just keeping the telescope working and keep the science going.
And everything looks excellent, and we have no reason not to expect that Hubble will last until the late 2020s and beyond.
My name is Mike Wins, and I'm the lead systems engineer for what's known as the Optical Telescope Assembly of the Hubble Space Telescope. I'm in charge of what's known as defined guidance sensors. These are the instruments that actually help Hubble do the exquisite and precise pointing that it does. Right now we're getting ready to perform an observation. The telescope is going to be trying to go to acquire some guide stars in just a few minutes here. The stock is the Space Telescope Operations Control Center, where we send commands to the spacecraft. On a daily basis, we have to send up what's known as command loads.
Accepted. DCMR is good. Step 3 is complete.
Because the computers on Hubble are very old and they have very little memory, in fact, most of your memory sticks today are 20, 30, 100 times bigger than Hubble, we have to send up essentially a load of all the commands Hubble's going to be doing for the next 24 hours.
On a routine basis, we always keep 24 hours of instructions on board, so it's routinely updating for the new sequence 24 hours in advance.
We'll start with doing our premise uplink.
Hubble is always working, it's always doing something, it's always doing some sort of observation or calibration or getting ready for the next task.
We'll be locking on forward at 14:33:17.
Hubble is truly a 24/7, 365-day-a-year instrument, so the Hubble can keep on going. It never stops.
And we are configured. It's been verified.
Now we do have to, because of this low Earth orbit we're in, the actual observations, when we're taking a picture of something, we're doing a science observation, we actually have to wait because sometimes the Earth gets in the way. So we have to pause, wait until the Earth gets out of the way as we go back around and start the observation back up.
You have constraints. You don't want the optics pointing at the sun. And you don't want the instruments to have their shutters open when you're looking at the Earth, because the Earth is bright for them. And then we have the South Atlantic Anomaly, the SAA, which is a portion of the Earth where we get proton hits that will affect the electronics in Hubble and can also affect the instruments in Hubble. And so we have to plan out very carefully our targets and observations. We have a timeline that's laid out to maximize the efficiency of it.
Hubble can actually take observations during day and night passes. Every 95 minutes, we go around the Earth. The batteries will charge from the solar rays during the day pass, and then at night, batteries power the observatory so we can continue observing. The scheduling with Hubble, we're trying to put it together as efficiently as possible, minimize our gaps. The goal is to constantly keep it busy.
We're constrained to a certain extent, but whenever we have visibility, we are observing.
The demand for use of the Hubble Space Telescope from scientists around the world is very high.
Hubble is at its most productive. It's got some of the best instruments that have ever been on board it. There's a very high demand. Hubble's performing exceptionally well.
2, 1, and liftoff of Space Shuttle Atlantis. The final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Since the final Space Shuttle servicing mission, we're using Hubble to get the best kind of science return we can from the suite of instruments that we have. So our focus now is on making sure we get the best science while it's still operating so well.
Luckily, at the end of the last servicing mission, we were actually left with a telescope in great condition, but Hubble is getting older and older. It's a very old telescope.
Now, 10 years after the last servicing mission, we can't rely upon servicing missions to fix things, so we have to rely upon our own ingenuity to be able to figure out if something does fail, what are the alternative paths that we have.
For the telescope to keep giving us this peak science, we need lots of things to be working together very well on the telescope. We need a pointing accuracy system that is outstanding and keeping that whole system healthy and functioning so that we can point Hubble very accurately even while it's whizzing around Earth in its orbit.
For the telescope to be able to do the science it needs to do, we have to hold it very, very steady. There is actually a little bit of motion. I mean, it's hard. We're zooming around the Earth at 17,000 miles an hour, so it's hard to hold the telescope perfectly like that. The gyros are working really good.
The gyroscopes can sense motion in each direction. And so because of the gyroscopes that we have on board and how sensitive they are in terms of sensing motion, that we can keep our cameras steady.
Gyros are very good at measuring these very small rates. The fine guidance sensors are actually sort of used, I always like to describe it as backseat drivers. And they constantly tap on the gyro's shoulders, it's about once a second. And they keep saying, turn left, a little bit more right, a little bit left, a little bit right. I mean, it must be driving the gyros nuts. So the fine guidance sensors allow you that really fine control, but actually it's the gyroscopes driving the telescope. And they're doing a perfectly good job here. Everything looks good, where our stars the right brightness. The reason that is because we need to make sure we have the correct guide stars. One of the things we look at is the brightnesses, and that's what we're measuring here. Those are about right for what the stars were. But also, we wanted to make sure they were exactly as far apart as we thought they were going to be. And it did. It did a check, and it passed a very, very tight tolerance check to make sure that those were the right stars. So we know we're locked up on the stars. We got a good lock here. The gyroscopes are very critical because to be able to move from one position to another position, the gyroscopes are the only thing that can tell us how we can do that. We have 6 gyroscopes on board Hubble. Currently, 3 of them are still working. And 3 is sort of what people used to think of as the minimum number, but we have developed a science mode where we only need 1 gyro.
A big part of our job is to make sure that we can extend the life of Hubble and continue doing the high performance science that we're doing for many more years.
And what we've done is we've gone through all the critical components of Hubble and said, how can we potentially make them last longer, as you might do with your own car as it's getting more miles on it. The gyroscopes have been our most problematic piece of hardware, so I helped lead an effort to develop a 2-gyro science mode. And we were able to use that mode on orbit and be able to perform science. And then learning from that, we actually developed a 1-gyro science mode that we've been able to test on orbit, but we haven't been called on to use. But in the end, possibly 5 to 10 to 15 years from now, when we're down to potentially our last gyroscope, that is the mode we will be in. Before we do anything on orbit for the first time, we have to test it out on the ground. And we're very lucky to have what we call the VEST, the Vehicle Electrical System Test Facility. And the key with the Vehicle Electrical System Test Facility is it's an exact copy of the main part of the telescope where all the electronics are. And it has the mechanical bays, it has the computers, the electronic boxes installed in there, and it has the cables and harnesses in there. And in fact, when we were building the VEST, we had the quality engineers came to us and said, "You're not doing these cables exactly the way you should be doing them. You know, we've got better standards now." And our thing was, we're trying to build a copy of what we have on orbit. And so what you have in the VEST is an exact electrical copy of the Hubble Space Telescope. Every orbit as we come around the Earth, to be able to get our attitude correct, to get ourselves steady and locked on, the fine guidance sensors and the gyroscopes are key to that. And that's why those are the two of the subsystems that are on the top of our list as far as having contingency plans for and monitoring the health and safety of those and making sure we have them in peak performance. When something fails on Hubble, or we have an anomaly, something we don't understand, one of my jobs is to bring together the experts, which may be a thermal engineer, a mechanical engineer, an electrical engineer, a software engineer, all these different people. And we'll say, you know, how do we deal with this issue? And how can we work around it and return back to peak science? What you do is you come up with a list of what is available to you on the telescope in terms of potential. I could close this relay or open that relay or turn on this box. And I am continually amazed. You have a telescope on orbit that you can't even see. I mean, all you're doing is looking at the data coming down to you from the ground. These experts are able to use their ingenuity and come up with ways to continue to operate Hubble. And everything looks excellent, and we have no reason not to expect that Hubble will last until the late 2020s and beyond.
I personally am extremely grateful to the Hubble operations team, these people who work day and night to keep Hubble operating, providing exquisite science return, giving us the information that we need to know how Hubble's doing. Is it doing the kind of accurate pointing that we need? Is it getting the sensitivity in the various wavelengths of light in the various instruments that we need to have to do the science? Are we able to calibrate those observations in an accurate way? We couldn't do any of those scientific analyses if we didn't have this team of operations experts behind the scenes making sure that the details of Hubble's technical operations are being monitored, being handled, being managed, being planned in a near perfect way. Because the Hubble Space Telescope is so scientifically effective right now, scientists are using Hubble to investigate some of the deepest mysteries of the universe.
One of the primary things Hubble has been doing is looking at the atmospheres around exoplanets.
If you had asked the guys who built Hubble and designed Hubble, they would have sworn Hubble could never, ever do this.
That's one of the things I love about Hubble, is that it ends up giving us new questions, new mysteries to explore.
My name is Larry Dunham. I'm the Chief Systems Engineer for Flight Systems here on the Hubble Space Telescope. I started on the Hubble program back in the summer of 1982 when Hubble was being built out in California. First telescope in space to be designed so that we've got what we call orbital replacement units. They're modular boxes with handrails on them so the astronauts can go up and just pick and play. They've got nice connectors on them that make it easy for the astronauts with their big gloves to be able to put them in and out.
We've had 5 servicing missions. We have replaced some equipment multiple times, especially the instruments. We're always going with the advanced technology.
The telescope we have today on orbit is not the telescope that we launched originally. We've been able to replace all 5 of our science instruments with instruments that have the technology that didn't even exist when Hubble was being built originally.
The Hubble Space Telescope is really an observatory because it has several science instruments, several modes of operation. We have multiple cameras, multiple spectrographs. They each have different capabilities in terms of their sensitivities or the kinds of frequencies they can receive the electromagnetic spectrum. We can also use Hubble in different kinds of intriguing modes depending on what we're trying to observe.
There are different types of observing scenarios, and one of the things the scientists have been able to do is they've been able to come up with very interesting and unique observing scenarios that allowed them to do science that they never thought they could do before.
Because the Hubble Space Telescope has been operating for a long time, it's giving us what we need to explore the universe in deep ways that would never have been possible when Hubble was first launched. For example, scientists wondered whether we could use Hubble in an innovative mode in recent years, basically scanning objects slowly instead of just staring at them. In some cases, that gives us a higher sensitivity to what we're trying to observe. And we're using that special mode on Hubble now to get better information about many types of things in space, including to be able to study planets around other stars, what we call exoplanets, planets outside of our own solar system.
What Hubble's been able to do is as the planets go in front of the stars that they're going around, the spectrographs can detect changes, very small changes in the spectrum. This has allowed them to do exoplanet atmospheric studies. This is something that Hubble has sort of really stepped up to the plate and has been just phenomenally good at. Spectrographs have really sort of been leading that. If you ever see things about, oh, a new exoplanet was discovered that has this in the atmosphere or that in the atmosphere, or we think it's made of this, it's the spectrographs which have shown you that kind of information. For doing a lot of the exoplanet observations, you have to catch what's known as a transit. One, the orbit of the exoplanet has to be such that it's going to go between you and the star it's going around. We can't just do an exoplanet observation whenever we want or whenever it's convenient. We have to do an exoplanet observation when it's first starting to go into the star. And so they have to know very accurately the timing of that. We have to schedule it ahead of time. This is not something that Hubble can get around to when it wants to. We have to say, no, at this point in time, on this date, you have to be pointed here and you have to be looking here. We had to really think about how to schedule this. A lot of thought goes into it. A lot of thought goes into the planning and of the execution.
The Hubble operations team are quite willing and capable of using the telescope in new modes and new innovative ways that enable us to accomplish science that we wouldn't otherwise be able to accomplish. We asked them, would it be possible to use Hubble to track something moving quickly across the sky? And they figured out a way to use Hubble in a vast tracking mode that enabled us to do explorations and discoveries that astronomers didn't envision using Hubble for when it was first designed.
Now, when we're observing our planets, when we're observing Jupiter or Saturn or Uranus or Neptune, they move also. We have to move the telescope because they're just going around the sun. They're actually moving because they're really moving. So we have to move with them. We're observing asteroids or comets. We have to chase after them.
Oumuamua, we know came from outside of our solar system, is like a big asteroid that was detected whizzing through our solar system. We wanted to use Hubble to observe this as well, and we were able to track it. This is not a simple operation. It's moving at more than 100,000 miles an hour, so being able to observe this and track it is a wonderful capability that the operations team has enabled Hubble to have.
The telescope is big, it's massive, it moves about the same speed as the minute hand on a clock. So to move from pointing one thing to go completely around the other one takes us a half an hour. It is not a very fast motion. We actually use a very interesting technique. It's using Newton's third law. We have these very large reaction wheels on it. They're about 2 feet across, very, very heavy, very, very massive wheels. You start spinning those wheels one way, the telescope will spin a little bit in the opposite direction. This is how we can move the telescope from one part of the sky to another part of the sky.
Once we've moved the reaction wheels and we've moved the telescope so we're in the right spot, now we have to get in the exact location to put the target in the science instrument aperture.
What's going to happen now is the FGSs are going to start talking to the telescope, talking to the flight software computer and saying, I want you to move the telescope over here a little bit to To be able to position the science for the science aperture.
Most of the time we use the Hubble Space Telescope to do observations that have been planned quite a bit in advance. Observers around the world, astronomers will write proposals. We will then take those accepted proposals and observe whatever it is that the astronomer has proposed. But sometimes there are things that happen that are unexpected or rapid events that we need a more rapid response.
We have a capability of what we call a target of opportunity. And that's when something unexpected happens in the universe that astronomers, they want to immediately jump on that as fast as possible with Hubble. Case in point was the gravitational wave detection to neutron stars colliding. A target of opportunity was submitted for Hubble to actually go look at the remnant and see if we could find it.
We had the engineers run through it. We got new commanding sequences from the Space Telescope Science Institute. We were able to run all that through, and then we executed on orbit.
We have to respond very fast. We produce a new schedule and set of command loads.
We can modify a lot of the flight software, modify how the instruments are commanded. It allows us to change. We can react very quickly. What Hubble has done compared to what we were thinking Hubble could do is just amazing. Hubble's had its fingers in almost everything, a neutron star collision, looking for all the supernova, all this stuff going on with dark matter, dark energy, exoplanets. Hubble has just been constantly finding new things. Now we're looking at these interstellar comets and these interstellar asteroids visiting us. It's really been spectacular to watch.
There really are two key aspects to Hubble's design that have enabled us to last the 30 years that we have, and that is really the redundancy that we have on board, and then it's the servicing, putting in new and improved instruments and being able to improve the hardware with lessons learned over the 30 years of Hubble operations. We are now at our peak performance.
The Hubble Space Telescope has had a profound impact, not only on astronomy. It showed that humans in space and science can go hand in hand to enable us to explore space in richer ways than we could ever do with either just astronauts alone or just with instrumentation alone. By using these skills together, new vistas of exploration are open to us, and that lesson is something we're still benefiting from as we envision future space exploration.
Go ahead. Okay, we have a go for release. Okay, Charlie.
It's amazing with a program that's lasted the duration that Hubble has lasted, that the astronomers up at the Space Telescope Science Institute continue to come up with new things that they want to try to do with Hubble, and we certainly hope that we'll be able to continue to provide that kind of capability to them into the late 2020s and beyond. What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
The Webb telescope will be groundbreaking because it has capabilities that are different than the Hubble Space Telescope.
We have equipment that is so much more powerful than anything we've ever had before that it's almost impossible to tell what we will discover.
Hubble's accomplishments include something called the deep fields, looking out into space and collecting light, sometimes for many days. These deep fields have revealed visually to us a universe absolutely teeming with galaxies, hundreds of billions of galaxies.
One of the neat things about the ultra deep field, and one of the things that made it so unique was how long it took us to take that image. There's an exposure time that's expressed, I think it's 11.2 days. There's a very, very long exposure time. But probably what's more important is how many orbits it took us to do that. 400 orbits of Hubble data to take that image. You only get 15 orbits a day. To take 400 orbits and say, we're going to observe this one spot in the sky for 400 orbits. And the really unique thing about that was they picked a spot where there wasn't anything. looked and they said, there's absolutely nothing here. And they said, you want to spend 400 Hubble orbits looking at nothing? And they said, yes, because we want to see what it can see. And I think the results from the science, I mean, it was amazing. What they saw was spectacular.
Hubble had spent 2 weeks taking pictures of empty places in the sky, and they saw they weren't empty at all. They were thousands and thousands of galaxies.
We were amazed how many galaxies we've found, and we continue to go back to that portion of the sky to increase that visibility.
The Hubble Space Telescope is an outstanding time machine. It's incredibly important for our studies with the Hubble Space Telescope to realize that when we're looking at a galaxy, we're seeing it as it was millions of years ago, sometimes billions of years ago. It's taken that long for the light to get to us.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
What Hubble has revealed is that the universe has in fact changed over these billions of years of time. The early galaxies, the very distant ones as we see them, are simple. Sometimes they're messy looking, they're small, they haven't had time yet to form that grand spiral structure. Over time, we see galaxies actually merging with other galaxies and growing bigger and bigger, and those mergers can look like train wrecks in our Hubble images.
These very, very deep exposures that Hubble has been able to take, we have seen right to the edge of the universe, 13.5 billion years. When Hubble was first designed and envisioned, it was never thought it could actually see that far out. But because of the advances in the instruments that we've been able to put up on the telescope, and also the cleverness of the scientists, they've come up with very interesting observing scenarios, doing these really deep exposures where we just sit there for orbit after orbit after orbit, gathering the photons. We've been able to push Hubble out very, very far.
As Hubble looks out into these fields of galaxies, we sometimes see clusters of galaxies. These are galaxies that are held nearby each other by their mutual gravity. These clusters are massive conglomerations. There's so much mass that they have an actual observable impact on space-time itself. Einstein predicted that mass distorts space, but we didn't realize we could actually see the effects of that. But with Hubble, we have been able to see distortions in space around clusters of galaxies. The way we see that is when light from a background galaxy travels through that cluster of galaxies or around it due to this gravitational lensing effect. The lensing also magnifies that background galaxy, so if we look in some of these distorted arcs, we can see more detail than we would ever have been able to see without gravitational lensing, nature's boost.
There are observations where we're explicitly looking for the lensing, and they're getting science out of that just otherwise would just not be doable. Hubble has really taken that to a next level. It's doing large amounts of astrophysics that it's just never been able to do before.
Some of what we're doing with Hubble is to prepare for the new James Webb Telescope, which we anticipate launching in 2021, which will be able to see farther into the infrared part of the electromagnetic spectrum. That enables us to see some galaxies that are difficult for Hubble to see because they're so far away that their light is traveling through us through expanding space and gets stretched out into redder wavelengths, often far into the infrared part of the spectrum, even sometimes beyond what Hubble is able to detect well. The Webb telescope will give us more information about some of those very distant galaxies.
The James Webb Space Telescope is the follow-on telescope after the Great Hubble Telescope. It extends the discoveries of Hubble into the infrared spectrum region. We think that the first objects that grew out of the Big Bang material probably happened in about 100 million years after that start. And And we think the Webb telescope can pick them up. They're rare, they're hard to find, but they should be there. The farthest we've been able to see with the Hubble telescope goes back about 800 million years after the expansion began. So we think we get much closer to the first objects with the Webb telescope.
Hubble gives information that the Webb telescope cannot give about visible and ultraviolet emission from things in the universe. And when we have all that information coming in at the same time, it's like a banquet of scientific return.
Now when we get the complete picture of every wavelength you can possibly see from ultraviolet to infrared, we hope to have the story of the growth of the first galaxies from the primordial material. So that will be a huge accomplishment that depends on both pieces of equipment, the Hubble telescope and the James Webb telescope working together.
So astronomers are very excited about this probability that we'll have both the Hubble Space Telescope and the Webb telescope operating at the same time for quite a few years. That will give us an abundance of new understanding about the universe. And already right now with Hubble, we're doing preparatory observations for the Webb telescope. We're using Hubble to do things, for example, like surveying distant galaxies to find out which ones would be prime targets for the Webb telescope. In fact, scientists around the world are proposing observations with Hubble right now specifically to help us learn information that will be useful for making the best use of the Webb telescope as soon as it's launched and gets going in its science observations.
I think the Hubble telescope has been the most productive science instrument ever built. In astronomy, there's what we knew before Hubble, and now there's what we know after Hubble. They're so different. Of course, Hubble has now had a life of 30 years, so it's had a long time to make this revolution happen. So it's not all at once. It's a gradual revolution, but it's still a huge revolution. Technology has changed dramatically over the 30 years of life of the Hubble telescope. So you couldn't even have imagined when the Hubble was launched that we would have the wonderful cameras and spectrometers that we fly today. We figured out how to send astronauts, we trained the astronauts, we figured out what instruments could be put in, we figured out how to repair everything that went wrong on the Hubble, and it's still alive. It's today, 30 years after launch. And I am so thrilled to say that our people were able to do that. That's the operations team that makes this possible. It's a miracle as far as I'm concerned, because it didn't have to be that way, but they made it happen.
It's all about the Earth and what we can learn about it from the International Space Station. Hi, I'm NASA astronaut Tracy Dyson. Welcome to Station Life.
Center 2 for velocity calculation station assembly, steps 4, 5, and 4, 6. We're moving on to step 5.
You want to go right now for that activity?
Copy, thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
Welcome back. This month on Station Life, we're going to highlight the International Space Station as a platform for studying the Earth and take a behind-the-scenes look at what it's like to live and work aboard the International Space Station. You know, they say a picture's worth 1,000 words. The first pictures taken by humans from space forever changed the way we view ourselves and our world. If you've ever flown on an airplane in the window seat, you know the natural desire to stare out the window. Well, aboard the International Space Station, one of our favorite things to do during our off time is to stare at the beauty of our home planet.
Take a moment every day to look out the window and appreciate where you are.
Literally watch the Earth go by. We're going around the Earth once every 90 minutes. So you see a sunrise and a sunset every hour and a half.
It's just so vast and so vibrant in color, and so much contrast between the black that it kind of overwhelms you at first.
Don't just look out the window during the day. Go for the times between day and night and then night and day, and take some time to look out into the universe at nighttime, because that's when you can really see all the stars. And you can see that the stars are not only like in a planetarium where they're sort of in a 2D field, they're actually 3D, and some are farther than others.
But you could see the blues and the oranges and the reds and the whites and the yellows, and really see more color about the stars, which indicates more about where they are in their life cycle, what kind of things they're burning and doing. And you would think that you'd get tired of looking out the window, but you never do.
Like I said before, a picture's worth 1,000 words. But in the case of International Space Station imagery, a picture could also be worth 1,000 lives. An imaging system aboard the station called Environmental Research and Visualization System, ISERV, captured photographs of Earth from space for use in developing countries affected by natural disasters. This is yet another way the orbiting laboratory is serving humanity off the Earth for the Earth.
SERVIR is a joint NASA and USAID program where we're working with developing countries around the world and strengthening their ability to use satellites to address the many problems that they have, including floods, fires, harmful algal blooms, and other types of events that they have where they can use satellites to really make better decisions.
We're using space information to help decisions that affect people in the village where they live.
When there's a major disaster, governments around the world come together and they provide all of the satellite data basically that the world has to offer. But there's smaller disasters that occur in the countries that we work in that may not make the front page of the New York Times, but in that country it's a really big deal. We asked ourselves, could we make a difference if we had a dedicated imager for acquiring imagery quickly after natural disasters, and to be able to provide that imagery back to the countries that need them, that have real decisions that need to be made with a very quick turnaround. As NASA, we looked in our own backyard and started thinking, could we use the International Space Station? The International Space Station was really a fantastic asset to take advantage of because it passes over 90% of the Earth's populated area every 24 hours. We developed an imaging system and we called it ISERV, which basically is a camera and a telescope system that sits inside the International Space Station and can collect imagery when it passes over natural disasters or other events that we need to collect imagery.
Initially, we were planning to take a few pictures per day.
So we contacted all the USAID missions around the world, and in total we had more than 2,000 requests coming, for people who need images from ISERV.
And we moved to like 1,000 images per day.
We provided ISERV imagery for many, many natural disasters, including floods and fires, for deforestation, for volcanic eruptions, for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
And now we have a huge archives of images of areas around the world. So this is something that was not really there before.
ISERV is an example of, in essence, making the International Space Station even more international and connecting space to village to better understand and protect our home planet.
Imagine bread loaf-sized satellites zipping around the Earth each day, imaging the globe and providing updates on the environment. Thanks to the International Space Station, this constellation of satellite image gathering has been made a reality. With the mission of photographing the majority of the Earth every day, Planet Labs created small satellites, individually referred to as doves, to capture ground imagery for use in humanitarian, environmental, and commercial applications. With the 2005 NASA Authorization Act designating the U.S. segment of the station as a national laboratory, the space station drives growth of a robust commercial marketplace in space through endeavors like Planet Labs. The Earth imaging mission of Planet Labs' Dove satellites takes another leap toward creating benefits on Earth, resulting from innovation in space.
What happens if you wake up in the morning and you understand the state of the world as it is right now?
What could that data enable? How could people make smarter decisions? How could, for example, a farmer get better yield on his or her crops? How could somebody help disaster response? How can we use satellites to help humanity? That in many ways was the underlying thesis of doing Planet Labs, was to get data into the hands of people that could enable us to make smarter responses to that.
Planet Labs set out with the mission to photograph the entire Earth every day. And they thought, how are we going to do this? They said, let's build our own satellite.
Commercial imaging satellites, they're very large. They are very expensive. We took a different approach.
By making them really small, we can launch lots of them, and by launching lots of them, we can cover this, to get to this mission of imaging the whole Earth every day.
If we can do that, then we can literally change the way that we see the world.
And they called it the Dove. It's about the size of a loaf of bread.
Our doves are basically mainly a big camera with a telescope looking down to take pictures of the Earth. We initially developed the first Dove satellite in our garage. So we kept on iterating the Dove design, we made it better and better, and eventually we put our first one into space. We had no idea what the quality would be like.
I mean, we didn't know if it was going to work.
But we got an image down and it was so beautiful that we knew at that point we could make this technology work.
Wow, we can really do this, and we can achieve this mission, which is something that is really needed for us to understand global change.
So we had done a couple of demonstration satellites, but the next steps we wanted to do was to scale it up, to test the first fleets of satellites.
But what made that possible was actually access to space.
So here's the problem, that in order to take pictures of the entire Earth every day, you're going to need more than one or two satellites. You're going to need a whole lot of satellites, and you're going to need to be able to deploy them really fast. And really, there's only one obvious choice on how to deploy that, and that's the International Space Station.
There was no other platform in the world in order to get access to space of that fashion in that time period than the International Space Station.
NanoRacks is our key partner with NASA.
At NanoRacks, we understood Planet Labs' vision, and we knew that we could help. We worked together to figure out what was going to be the best way to get as many satellites as possible, and we basically developed a new platform. It goes out of the GIM airlock, it's picked up by a robotic arm, pointed out into space, and it fires these little satellites off of the space station.
They were able to secure 28 of our satellites to be launched from the International Space Station, and that was known as Flock 1, our first constellation.
This opened up the whole world to satellite developers, people that could put things into orbit fast.
We now deploy these on a regular basis from the International Space Station. And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The International Space Station does enable young, small companies like ourselves to get going in space.
The ISS provides a lot of opportunities for commercial companies to test and find where the market in space is going to be.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
I used to think when I was growing up in Florida, lots of thunderstorms in Florida, you know, that here's this storm over top of me and it's just this individual little thing that just is about a storm over Florida. And in fact, now after looking at the Earth from space, I see that that little storm in Florida is connected to Africa and Europe and all across the planet. And one of the most impressive things to see is how the Earth presents itself as alive when you're watching these storms at night just trickle across the whole surface of the planet like its own nervous system. And the emotions of the Earth, you know, seeing storms that are developing and the way you know from having that experience on Earth how it's probably impacting the people and the places down there. It's like, oh, is it upset and mad today versus the sunshine over some other part of the planet? And really, really, really gets you looking at it in a different way, an appreciative and respectful way. When you're crossing the deserts in Africa and the way the dunes form, and they almost look like little, birds have run across the sand. And then this contrast you'll get from kind of the pinks and oranges and whites to these dark grays and almost deep blues and of rocks and everything that are intersecting with it. And the Bahamas and the northern coast of Venezuela, which quite honestly is, I think, the most beautiful place on our planet. It is just incredible. Yeah.
Well, so far we've learned about using the ISS as a platform for iServe, which captures imagery of the Earth to provide disaster assistance, and deploying small satellites called doves. We expect good things to come from both of these experiments and look forward to their robust potential. NASA has selected proposals for 2 new future instruments, Getty and EcoStress. These sensors on the ISS will give scientists new ways to observe how forests and ecosystems are affected by climate change. Our next piece is about a recently completed mission of an Earth-observing instrument on the ISS called HYCO. Its name stands for Hyperspectral Imager for the Coastal Ocean. Check it out.
Carroll Township's a very rural area in northern Ohio, right on Lake Erie. Lake Erie has always been very important to Carroll Township and its residents. We use it for drinking water, we treat it, and it's really our livelihood.
In Lake Erie, for what unknown reason, suddenly the toxin level spiked, and that got through the treatment system.
It was indicated to me that it is pretty dangerous.
Cyanotoxins can cause skin rashes,
Headaches,
nausea,
vomiting, stomach problems,
nervous system problems,
liver damage,
to death.
We sampled and we had about 2.5 times the limit from the World Health Organization. The second sample was approximately 3.5 times. Our plant wasn't set up to handle what was coming in from Lake Erie. One of my biggest worries was actually hurting someone or even worse. So we shut it off right away, shut everything off. We had a very close call that day. The last thing you want to do is produce an unsafe water and allow your people to drink it. What we need is a better way to track and predict these cyanobacteria entries from our source water so that we can make sure that this never happens again.
A lot of times we'll find out after the fact that there's a problem with cyanobacteria in the water because the blooms already occurred. We either get results of sick animals or sick people. We need a paradigm shift. We need to go from being constantly reactive to these blooms to having a capability that allows us to become proactive. And the U.S. Environmental Protection Agency has been very encouraging of allowing for some high-risk, high-reward projects. And that allowed us to think outside the box, way outside the box. We've been fortunate enough to make use of a sensor on the International Space Station called HYCO, which stands for the Hyperspectral Imager for the Coastal Ocean.
HYCO consists of 2 instruments. One is a camera, and the second instrument is a spectrophotometer, which actually gives us the spectrum of light leaving that water.
The camera on a cell phone, for example, contains about 3 bands of data in a red channel, a green channel, and a blue channel.
HICO gathers light from the red, orange, yellow, green, blue, indigo, and violet parts of the spectrum. So using this technology, we're able to now detect those water quality parameters such as water clarity, what the phytoplankton concentration is in your water, how much light is being absorbed in your water, as well as what's the distribution of cyanobacteria in those waters, and does that concentration pose a health hazard?
So what this means is instead of waiting for someone to report that there's a problem with cyanobacteria bloom, we can monitor these water bodies from space
and get information that we can rapidly get out to the water quality managers through a smartphone application that we've developed.
So the app allows you to drop a pinpoint, and that pin can be placed in an area where a drinking water treatment plant may have an intake, and see what the current water quality conditions were. Each user gets that information near real time, so they can make judgment calls on whether they have to respond or take action.
Having the HICO on the International Space Station has been the ideal test bed for our research.
This is an amazing partnership. The Naval Research Laboratory had HICO on NASA's International Space Station. As HICO acquired a scene, it was transferred to the Naval Research Laboratory. And then the Environmental Protection Agency was able to do the analysis and the validation to send this information out through a prototype mobile application. Yes, this technology will reduce costs and provide near real-time information. But the big goal here is protecting humans. And if we can reduce exposures both to humans and even animals, then we've achieved our goal.
Our International Space Station is an unprecedented research platform in space, allowing researchers and scientists to conduct experiments that can't be done anywhere else. Utilizing the ISS as a ready-built platform for studying the Earth is well underway. So far, we've learned about iServe, Planet Labs' Dove satellites, and HICO. 2 more experiments, or payloads in NASA speak, are on schedule to get to the ISS later this year. There's SAGE 3 and Lightning Imaging Sensor. SAGE 3 will measure ozone and other gases in the upper atmosphere to help scientists assess the ozone layer and how it's recovering. And the Lightning Imaging Sensor will monitor global lightning for Earth science studies and support operational weather forecasting and warning. Looks like utilizing the ISS to further benefit all of humankind? It's right on track. Thanks for joining us on Station Life at our behind-the-scenes look at using the International Space Station as a platform for studying the Earth. And be sure to follow us on Facebook and Twitter for the latest research news. And don't forget to download our straight-up gangsta app on your mobile device. It's totally legit. Until next time, we're working off the Earth for the Earth.
Are we dressed up right here?
Yes.
You guys meet?
Alright, guys, I need you to be quiet though in the other room.
Okay.
Okay, got it.
Alright. Okay, we're doing it.
Pretty much anything that you can observe on the land and coasts, and sometimes even in the ocean, NISAR will have an application. Very exciting mission, generating an enormous amount of data that will keep the science community and the applications community busy for a long time.
NISAR is a partnership mission between NASA and ISRO, the Indian Space Research Organization. It's a collaborative project.
And we'll be collecting data for all around the whole Earth for all of the land masses.
Looking at volcanoes, earthquakes, landslides, other natural hazards that occur in the crust of the Earth.
A movement of sea ice, movement of glaciers, how much forest land is growing or being reduced.
Because it can image at night and through clouds, it can allow us to see through storms.
It's really going to allow us to see things changing in areas where we can't with other satellites.
So NISAR is going to open our eyes to the potential of this technique for seeing the ground in places that otherwise has been obscured.
So every 12 days we will map the land masses, and then we can take those mappings and we can compare them. We can do what we call interferometry,
where we can take an image acquired on one day and combine it with an image acquired 12 days later from that same vantage point, looking at the same point on the ground. And when we do that, we can see the motion of the ground down to a fraction of the radar wavelength, which in this case is on the order of a few millimeters.
NISAR has two radars on it, two synthetic aperture radars. One is an L band and the other is an S band.
So it's kind of the Tesla or the Maserati of radars, whichever you think is cooler, I guess.
This here is the radar payload. That is the spacecraft bus. Large 12-meter reflector, common antenna system for both L band and S band to send out the RF signal and capture the return signal.
Good morning, Dr. Paul.
Antanu, how are you today?
Yeah, I'm fine.
The pandemic is something that we were not counting on when we developed this project.
The NISAR project was actually pretty well versed with this remote operations because of that Indian engagement.
There was a little bit of WebEx fatigue, but I think we're learning how to do it better now.
But yeah, we're all in great spirits, and we will take a little hit to the schedule, but we've been waiting a long time for this mission, and we want to do it right. We want the hardware to work, and we want the science to be done.
One of the best things we can do to increase diversity in the sciences is to make it easier for people to enter the sciences.
The data is going to be freely available to everybody. We aren't going to have to pay for it like we do with some satellites.
So making the data free, having it easy to download to your own machine, all of that stuff is critical if we want to remove those barriers to entry to the field.
I'm looking forward to the sense of discovery that I think we're going to have when NISAR data start coming down.
Earth science is incredibly important to understand what's going on in the name of what our children and grandchildren are going to have to face in the future. And all the information we collect now is only going to help them understand that better and hopefully make their lives better.
Digital electronic subsystem, cognizant.
There goes my son.
You know, the radar will...
I can't recall... There we go.
That's our real life here in 2020.
It's a bittersweet privilege to be taking Endeavour on its last flight, delivering the last major piece to the ISS.
I was there before they put the wings on it. It was just, so it was almost like it was my baby.
That space station assembly mission was perfect from start to finish, and a lot of that was Endeavour. It just, phenomenal vehicle.
The eagle represents, the United States of America. It's something we're proud of. That's our bird. That's the eagle.
After nearly 2 decades of achievements in space, Endeavour makes one last reach for the stars on its 25th and final mission. Endeavour is traveling to the International Space Station with 6 veteran space flyers, Commander Mark Kelly, pilot Greg H. Johnson, and mission specialists Mike Fink, Drew Feustel, Greg Chamatoff, and Roberto Vittori from Italy, representing the European Space Agency.
Well, I'm the commander of STS-134. We've got a whole list of mission objectives, probably 30 things on the list. But the big objectives is to get the alpha magnetic spectrometer installed on the outside of the space station.
The 15,000-pound AMS is a massive particle physics detector that will attach to the International Space Station. Its job? To search through cosmic rays, looking for proof of dark matter and antimatter.
In my mind, this is like the Hubble Space Telescope. I mean, it has the same type of potential for revolutionizing our understanding of the universe.
They're also delivering critical spare parts to help keep the station up and running for years to come, along with the shuttle's orbiter boom sensor system. Feustel, Fink, and Chamatoff will rotate through 4 spacewalks, the last performed by shuttle crew members for the remainder of the Space Shuttle program. And when Endeavour makes its final touchdown on the runway, it will end a storied flying career for the youngest of NASA's shuttle orbiters. Even Endeavour's beginnings were unique. It was built as a replacement for Space Shuttle Challenger, a name for the first ship commanded by explorer James Cook. At the time of the Challenger accident, astronaut Barbara Morgan was part of the Teacher in Space program, serving as backup to teacher Krista McAuliffe, who launched aboard Challenger on that fateful day in 1986.
I think Endeavour in particular, because she was named by school children all over the country, that really shows a carrying on and a moving forward, and how open-ended and never-ending that future can be.
Like all shuttle orbiters before it, Endeavour was built by Rockwell in Palmdale, California. That's where astronaut Bruce Melnick's bond with Endeavour began.
My first job as an astronaut, even before I was a qualified astronaut, was to represent the astronaut office out in Palmdale, where Endeavour was being built. So I got to see her being built from scratch to finish, got to see the wings put on, and it's amazing.
The nation's brand new space shuttle was delivered to Kennedy Space Center on May 7, 1991, exactly 1 year before its maiden flight.
It was great to see Endeavour come in. We knew why it was coming, because it was replacing Challenger. So it was going to be the new fleet leader and the new kid on the block.
Melnick was on Endeavour's first flight, STS-49. The 7-person crew faced an ambitious 8-day mission to repair the stranded Intelsat 6 satellite.
I'll never forget when Dan Brandenstein, who was the chief astronaut at the time, asked me if I wanted to be on the first flight of Endeavour. I mean, you could hear me hooting and hollering, because that was going to be the premier mission at the time.
Endeavour made history again during the last shuttle mission of 1993, when 7 astronauts upgraded the Hubble Space Telescope and improved its vision. It was an extremely complex flight, involving 5 back-to-back spacewalks. And in the end, all the hard work paid off. The telescope's new second-generation wide-field and planetary camera beamed back grand images taken with dazzling clarity. And Endeavour helped to carry the load in the construction of the International Space Station, including the very first shuttle flight to the fledgling outpost, STS-88. Endeavour delivered the American Unity module, and astronauts connected it to the Russian Zarya module already in place, and the station was born. Kennedy Space Center Director Bob Cabana commanded that cornerstone flight.
I have to admit, because I got to command Endeavour on that first space station assembly mission, I'm a little partial to Endeavour.
But less than 3 years later, the nation was stunned by the terrorist attacks of September 11, 2001. On December 5th, all eyes turned to Kennedy Space Center, where Endeavour waited to make the first flight after the tragedy.
Mike, first, we'd like to say thank you to the entire KSC team for getting Endeavour in great shape. And secondly, from the entire crew, we're all well aware that for over 200 years, and certainly over the last 2 months, freedom rings loud and clear across this country. But right here and right now, it's time to let freedom roar. Let's light them up.
1, We have booster ignition and liftoff of the Space Shuttle Endeavour, pushing our goals skyward using our station in space. Endeavour lifted the nation's spirits with a spectacular launch at the twilight's last gleaming. After 2 more flights, Endeavour entered an extended downtime for planned maintenance and upgrades, including the new glass cockpit and a global positioning system for landing.
I think the missions you remember the most are the missions that were the toughest to get there, but we met our goals on the way. You know, we powered up in time after coming out of a major power down period and the major upgrades with the glass cockpit.
The newly upgraded orbiter returned to service in August 2007 on the STS-118 mission. Morgan flew as a mission specialist and recalls watching an orbital sunrise.
So I looked back up at the horizon again, and there was a crescent moon. And it literally seemed, even though it's not this easy to do, but it literally seemed all we had to do was yank on the tiller, take a right turn, and sail straight to the moon. And that's when I really understood how natural and how right space exploration, human space exploration is. And Endeavour played a big part of that.
STS-134 will be Endeavour's 12th flight to the International Space Station. One of the most memorable deliveries was its most recent, the cupola with 7 windows, offering astronauts a room with a captivating view of their home world. After 30 years, the shuttle program is coming to a close.
When you look up and you see that vehicle take off a launch pad, I mean, it's just such a sense of pride, and you feel the shock waves hitting you in the chest, and it just vibrates you. It just brings a tear to your eye that, you know, we're a part of that program. And then to see Endeavour go up, the last ship that I flew, and I was on her maiden voyage, and she, you know, treated us so well. To see her go into space for the last time, knowing that she's going to be retired after this flight, is going to be a real sad day.
The vehicles we see, you know, every one of the vehicles, including Endeavour and Discovery and Atlantis, they're all part of us, and they all are, you know, they're alive, and they represent each and one of every one of us that had worked on them.
The close-knit shuttle processing team is adjusting to the shuttle's end while still maintaining laser-sharp focus on the job.
You know, personally, we do have to think about putting our emotions aside. We have our job number 1, which is to get this vehicle prepared safely for the mission at hand with STS-134 launch.
But the toughest moment will be that final wheel stop when Endeavour returns to Earth for good.
Houston Endeavour, wheel stop.
Roger, wheel stop, Endeavour. Welcome home.
I didn't want to get out of the seat. I mean, this was my spaceship. You know, it really, that was hard getting out. In fact, of all the things I've done, it was hard. Getting out of that seat and giving Endeavour back to the team was, that was tough.
When Endeavour flies for the last time, it'll be show respect for everything that we've done for many, many years. We love the shuttle program, and we love this vehicle. And any vehicle that flies has to, you know, prove that it's flight worthy, and Endeavour did that. It's been a great vehicle.
Start. 6, 5, 4, 3, 2, 1. Booster ignition and liftoff of the maiden voyage of Endeavour on a satellite rescue mission.
For the past 2 decades, Space Shuttle Endeavour, the youngest vehicle in NASA's shuttle fleet, has symbolically carried the torch for Challenger, the orbiter it replaced. NASA is preparing for the final flight of Endeavour, a trip to the International Space Station during a time frame in which astronauts and cosmonauts are celebrating the 50th anniversaries of the first human spaceflight by Yuri Gagarin and the first American spaceflight by Alan Shepard, as well as the 30th anniversary of the first space shuttle flight, STS-1 Columbia. This historic 25th flight of Endeavour will include delivery of the Alpha Magnetic Spectrometer, a unique instrument that is hoped to unveil clues to the origin of our universe as it searches for antimatter, dark matter, and exotic cosmic particles from the space station. When Endeavour launches on NASA's 36th mission to the ISS, the STS-134 crew of 6 astronauts will begin a mission to stock the station with spare parts and a world-class stellar research instrument just months before the shuttle program comes to an end. Endeavour will deliver the Alpha Magnetic Spectrometer 2 and the Express Logistics Carrier 3 to the station. This will also be the first shuttle flight to conduct a re-rendezvous, but not dock to the space station, to test the performance of new navigation sensors designed for the Orion spacecraft. During 4 scheduled spacewalks, Endeavour's crew will conduct the last spacewalks by shuttle crew members to prepare the ISS for its next decade of service.
I've flown on Endeavour before, so I'm excited to fly on it again. And my brother's flown on Endeavour.
Navy Captain Mark Kelly is the commander of Endeavour's crew of 6 astronauts. He flew on Endeavour as the pilot of his first space flight, STS-108, in 2001. In January 2011, Kelly's wife, Congresswoman Gabrielle Giffords, was critically wounded during a community outreach event in Tucson, Arizona. Kelly took a brief leave from the agency, but returned to mission training a few weeks later. The pilot of Endeavour is retired Air Force Colonel Greg H. Johnson, making his second spaceflight. He will be at the controls as Endeavour undocks from the station. He flew on Endeavour as the pilot of STS-123 in 2008. Air Force Colonel Mike Fink is Mission Specialist 1. A veteran of 2 long-duration missions on the International Space Station, he commanded the station complex on Expedition 18. During this mission, his first aboard the shuttle, he will conduct 3 spacewalks. Mission Specialist 2 is Italian Air Force Colonel Roberto Vittori, twice flown aboard a Russian Soyuz as an ISS visitor and part of the crew that delivered fresh Soyuz spacecraft to the outpost. As the last non-American astronaut scheduled to fly on the shuttle, Vittori will meet up with Paolo Nespoli on the ISS for 2 Italian astronauts on orbit at the same time. Dr. Drew Feustel, Mission Specialist 3, is making his first voyage to the ISS after performing 3 spacewalks during STS-125, the final Hubble Space Telescope servicing mission. On this flight, he will serve as lead spacewalker for 3 additional EVAs. Mission Specialist 4 is Dr. Greg Shamatoff. He served as an ISS flight engineer for 6 months during Expeditions 17 and 18, returning to Earth on Endeavour. He will perform 2 spacewalks.
We've got a whole list of mission objectives, probably 30 things on the list. But the big objectives is to get the Alpha Magnetic Spectrometer installed on the outside of the space station.
The Alpha Magnetic Spectrometer 1, a simplified cosmic ray detector, flew on STS-91 in June 1998. The AMS-2 is a first-of-its-kind instrument designed to study the fundamental nature of the universe and will allow us for the first time to search for antimatter and dark matter theorized to exist. Nobel physicist Dr. Samuel Ting leads the team of over 500 scientists from 16 countries.
I started studying physics. Soon after I achieved my degree as a test pilot, I went back and complete my degree. And ironically, my teacher was Professor Battiston, that is the deputy chief of the AMS experiment. So it may appear as a very strange coincidence that today I will be the one to take this unique piece of hardware, take it from the bay of the shuttle and give it to install on the station.
On Flight Day 4, Vittori and Feustel, operating the shuttle arm, will grapple the AMS-2 and hand it off to the Greggs, Johnson and Shamatov, operating the station arm for robotic installation onto the station's S3 truss. The second of two components that Endeavour's crew will attach to the ISS is the ELC-3 pallet, the Express Logistics Carrier 3. ELC-3, similar to ELCs 1 and 2 delivered on STS-129, includes a full ATA, ammonia tank assembly, 2 SASs, S-band antenna support assemblies, and a spare arm for Dexter, the special-purpose dexterous manipulator. On Flight Day 3, Vittori and Fink will unberth the ELC-3 with the shuttle arm and hand it off to station arm operators Shamatov and Johnson for installation on the station's P3 truss. STS-134 will be the first shuttle flight to re-rendezvous with the ISS and to fly a rendezvous trajectory to mimic Orion's trajectory. The purpose of STORM, Sensor Test for Orion RELNAV Risk Mitigation, is to evaluate the performance of Orion relative navigation sensors for future spacecraft. While Kelly is flying Endeavour, Feustel will monitor STORM sensors from a laptop on the flight deck during rendezvous, undocking, and the re-rendezvous after the traditional ISS fly-around. Endeavour will pull away from station and execute several maneuvers before approaching on a different trajectory to allow the STORM vision navigation sensors to gather data. Although Endeavour will not actually redock with ISS, it will fly to a close approach of 1,044 feet below and 300 feet behind the station before executing a third separation burn and departing station for the final time.
Then when we come up back in front of the space station again, we're then going to do these series of burns where we're going to fall behind the space station, a couple 100,000 feet. And then we're going to come back in doing a profile that's actually quite similar to what Apollo used for a rendezvous.
During STS-134, Feustel, Fink, and Shamatov will take turns stepping outside the hatch for 4 scheduled spacewalks. EVA-1 on Flight Day 5 focuses on MISSIES, Materials International Space Station experiments. Feustel and Shamatov will return the MISSI 7A and 7B pallets from the ELC-2 and transfer MISSI 8 to the same location.
The idea is to expose these things to the harsh environment of space for a long period and see what happens.
For EVA-2 on Flight Day 7, Fink and Feustel will refill one of the station's port radiators with ammonia. They will also clean and lubricate the station's port Sarge, the solar array rotary joint. Prior to EVA-3, Feustel and Fink will test a new protocol combining the airlock campout pre-breathe, the exercise pre-breathe, and the spacesuit itself.
We were introduced to a pre-breathe option by Mike Gernhardt, an astronaut in the Corps, and it's called the In-Suit Light Exercise Pre-Breathe Protocol. We call it ISLE, I-S-L-E.
For EVA-3 on Flight Day 9, Feustel and Fink will install a power and data grapple fixture for the station arm on the Zarya module. They will also run 2 Y cables for redundant power supply to the Russian portion of the station. During EVA-4, Shamatov and Fink will transfer and install the OBSS, the shuttle arm's extension boom, to the station's S1 truss for potential future use aboard the ISS.
We have come very far in the last 50 years from not being able to fly in space to landing on the moon and building this incredible facility in orbit and routinely flying people up and down into low Earth orbit.
It is amazing how much we've accomplished in 50 years, and it took so many people to make all that possible. It's an unbelievable honor to kind of be the representative of that generation of dreamers for me.
We have a huge honor and responsibility to make this the best mission that we can, to honor all of the engineers all the way from the pre-STS-1 at the very beginning, in the 1970s when we started to design the space shuttle. All the effort, the blood, the sweat, the tears that have gone into making the space shuttle program as wonderful as it has, to fly on the penultimate mission and to do it well and to do it with the honor of those that came before us.
My land cover career really started in 2002 with biggest wildfire in Oregon's history, and that was the Biscuit wildfire. I, at the time, was doing botany surveys and looking for rare plants or rare mushrooms, and so I was spending a lot of time out on the forest looking at and taking photos and doing the documentation that a scientist or a land manager does. When that fire happened, it changed everything, because we all had to react to this fire that was burning up some of the places that I'd literally been the day before. And it was mapping what was there and what was under threat, but it was also mapping the effects of the fire. We needed to find a way to look across 500,000 acres. And the only way that we could really do that was satellite data. If we can't get out and actually measure every single thing, what are we missing? And that's where citizen scientists can actually come in and really help traditional scientists to better understand what is happening around them, but also fill in these gaps.
The Global Learning and Observations to Benefit the Environment program is an international science and education program. It provides students and the public with the opportunity to participate in data collection and the scientific process. The Globe Observer app is one of these opportunities, allowing citizen scientists and students to take land cover observations around the world and submit them to a larger database. But what exactly is land cover? Dr. Eric Brown de Colston of NASA's Goddard Space Flight Center explains.
Land cover is really the basic form of the landscape that we have around us. So whether it's a forest or a desert, but it's really one of the components of the landscape that we can study from space.
Dr. Peter Nelson is a scientist who uses land cover imagery in his research.
I am a remote sensing scientist who studies land cover across the globe. I use satellite imagery to make maps of land cover and try to quantify what covers the Earth. Sometimes a satellite can't see what's happening underneath a tree canopy or what's happening underneath cloud cover. And so we really need people to go out there and to take these photos, to do these observations, to help fill in where a satellite can't actually make some observations.
Just like any digital photograph, land cover images are made up of a series of pixels to show what covers the Earth. A pixel, or picture elements, is the smallest unit of a digital image. When combined with thousands of other pixels, a picture is formed. Each pixel color shown represents a land cover type. It's from these pixels where ground verification or ground truthing come into play. You see, depending on what satellite is taking images, a pixel can cover roughly an area of 30 to 500 meters squared. For imagery captured by Landsat, a pixel is 30 meters squared, or about the size of a baseball diamond. However, part of that pixel showing forest might actually be water, or shrubs. By taking land cover observations, citizen scientists can help answer these questions when it comes to land cover maps. So, why are these land cover observations so important? Why are they taken in the first place?
We also are looking at how these components are changing over time. So deforestation in the Amazon or across the world, how are cities expanding? A lot of different things to study, and really the view from space is the way that we do it here at NASA. We have big supercomputers that simulate the physics of the atmosphere and the land, the interaction between the Earth systems. It's important to have that, that land cover map. It sets certain parameters. Those models can actually be used to look at current day conditions and weather. So based on these current conditions, what might the Earth look like 50 or 100 years from now? There's an element of understanding, but then also being able to predict into the future, what that might be like, what these changes may mean for us.
Each point shown here represents a real-world measurement of environmental conditions. Scientists use computer models to fill in information where measurements may not exist. By verifying the satellite imagery and using the data for these models, scientists can predict changes in our environment more accurately. One of these scientists using land cover maps to track urbanization as part of her work is Dr. Amita Mehta of NASA's Goddard Space Flight Center.
So urbanization changes terrain as well as characteristics of the surface itself. And so impervious surface is what we look at when we are monitoring flooding. When there are, say, parking lots or cement and concrete surfaces, they increase. So previously, if it was a farmland or something which was not built, and if that is built now, that water previously that could go or percolate in the soil and in the ground now cannot go in, and it stays there. Monitoring helps you to plan for it. So if you see land cover changing, even then you know that how water is going to flow in that region might change. If you have to send rescue out or you have to plan for relief activities, then if you know land cover, then you know where there might be help needed.
By using land cover maps and models that reflect changes over time, scientists can predict where flooding and other events may occur. With a changing climate, these predictions from models and land cover maps can help scientists better understand these changes and help communities prepare for them. But perhaps a more important reason as to why take land cover observations is you get to participate in a community of scientists, citizen scientists, and students.
So it's a very important component that the citizen science and students of the GLOBE program and Globe Observer can contribute to is by really giving us the information on the ground of what they're seeing around them and in front of them. And we hope over time as well how maybe some of these things are changing, because those would be very valuable for science.
I saw the value of having information before a hazard happens, because once that fire went through an area, we can never recreate that data. This is all important for us to share and put together because that's how we understand Earth as a system. All of these things end up affecting where we live, why we live where we do, and why we make some of the choices that we do.
To learn more about Globe Observer, check out the website at observer.globe.gov and download the app to start taking your own observations today.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
Mission Control human spaceflight is made possible through the generous support of Alabama Bicentennial Commission, the Daniel Foundation of Alabama, Wells Fargo, the Malone Family Foundation, the Robert R. Meyer Foundation. Mission Control is a production of the IQ Learning Network, a division of Alabama Public Television.
You're looking good here. Roger.
Hi, I'm Dorian.
Carmen here.
This is Luke, standing by.
Here's Chandel. And I'm Kaylee.
We're interrupting your regularly scheduled programming for a very important reason. As members of the STEM Brigade, our mission is clear. Learn science, earn badges, and help others to learn too along the way. Right now, we're working on earning our cadet rank in space exploration, and our squad has a very important mission.
To learn all about the history and the science behind human spaceflight.
And as we sprint through this learning marathon, we'll try and earn 6 different merit badges: the space race, rocket boosters, shuttle, life systems, future exploration, and space computer controls. We'll be reviewing the badges we earn throughout the program, so pay attention and follow along, and you too can be honorary virtual members of the STEM Brigade.
We're ready to blast off. Mission Control, do you copy?
Since the dawn of humankind, the stars have been there waiting for us. But for the majority of human existence, leaving Earth was nothing more than the desire of an overactive imagination. If only they'd known, the stars have always been reachable. They were just waiting on us to find the right path.
Last century, following the birth of the airplane, scientists like Robert H. Goddard, perhaps the first great rocket scientist, started getting close. Rocket technology advanced quickly, especially during the Second World War, when rocket technology was used, regrettably, as a new kind of weapon. But from the dust of that terrible war came something better: the space race.
The space race was between 2 of the most powerful countries to emerge from the rubble of World War II, the Soviet Union and the United States. The space race ultimately amounted to a series of one-ups, as the Soviets and the Americans raced to see who could accomplish what amazing feat first.
The Soviets struck first, putting the first satellite in space, the first human, the first spacewalk. But the Americans were right behind them, step for step, thanks to early space programs like Mercury, which, among its many accomplishments, sent American John Glenn orbiting around the world. The 2 powers were both on a chase for the same finish line: who would be the first to get to the moon?
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
On July 20th, 1969, the Americans did the impossible.
That's one small step for man, one giant leap for mankind.
Neil Armstrong, along with Buzz Aldrin, became the first human beings to ever walk on the moon as part of the Apollo 11 mission. It was a day that changed the world. 2 men walked on the moon that day, but the support of thousands of men and women back on Earth put them there, and they all deserve credit for this landmark accomplishment of the human spirit. When astronauts say Houston into their radio, they're referring to Mission Control at Johnson Space Center in Houston, Texas. Mission Control has been the center of communication between Earth and human spaceflight from the early days of Gemini and Apollo to communication with the International Space Station today. I'm joined today by legendary flight director Gene Kranz, who was flight director of the Apollo 11 mission that first landed on the moon, and Apollo 13, where an explosion on board the spacecraft put Mission Control to the ultimate test. Thank you so much for being here with us today.
It's a pleasure to be here, and thank you very much for the opportunity.
What is the role of Mission Control?
Mission Control is the center where you pull all the people together, where you've got communications to the launch site, you've got communications to the tracking station. So it's basically the overall hub for communications. In addition to that, the controllers here are prepared to take any actions necessary for crew safety and mission success.
Could you tell me a little bit about your job as a flight director?
As flight director, I have the ultimate responsibility for performance of this room here. During the course of a mission, I am the final person to make decisions. There is no higher authority than me. And as mission time approaches, I look at the decisions I got to make and I see if I got a set of notes to fit that, and I write it down as sort of a timeline. Because the one thing I have to do in this room is to manage the clock. So it's up to me to know how to use every second that we've got in the decision process. Most of our decisions are hours. Frequently I'll get one that's down in the minutes. Ones that we do in seconds, I have to know instantly and tell the guy what I want done.
July 20th, 1969, moon landing. As the world watched, Houston waited for the call. What was the feeling like in this room?
That moment, that time in history, we knew that we had 2 minutes, 120 seconds of fuel in that tank at a 30% moderate throttle setting. So I had one controller in this room who had a stopwatch. He was counting out seconds of fuel remaining. Now at the time he's doing this, the crew is trying to go around and find their landing site. As he got down close to the surface, the dust on the surface was moving with him. So it was really hard to figure out, where can I land, and where's the right place to land, etc. And we kept calling out 60 seconds of fuel remaining.
60 seconds.
At about the time we said 30 seconds, we saw the crew going through engine shutdown.
30 seconds. Okay, engine stop.
And that's when we heard the word, Houston, Tranquility Base here, the Eagle has landed.
Tranquility Base here, the Eagle has landed.
And boy, all through this thing, I had a hold of one of these handles because in those last seconds, it was totally up to the crew. My job was over. I got him down close. He had to land. But I was holding on to that guy, and I don't think I took a breath. And that was true of everybody in this room.
Roger, Tranquility, we copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. Thank you.
Okay, Apollo 13, the infamous. Houston, we've had a problem. What was going on in your head at that moment?
You have to think your way through problems. So as soon as I heard that call,
Hey, Houston, we've had a problem here.
Earlier in my shift, I had 3 minor electrical problems. And my immediate thought is, it's a minor electrical problem, we'll sort it out, we'll put the crew to sleep, and then we'll work the problem.
Stand by, 13, we're looking at it.
Then about a couple minutes later, one of my controllers said there was a pretty big bang associated with that. The crew reported a bang, and I said, okay, something I don't understand is happening right here. I better proceed more carefully. And then about 10 minutes later, Jim Lovell's looking outside the hatch window, and he sees a jet plume going out there. And he says, Houston, I think we're venting our oxygen.
We are venting something out into space.
Roger, we copy your venting. And that was when I went into survival mode. Say, okay, I'll flight controller, settle down, quit your guessing, let's start working this problem. And that was really the key to getting this room now focused on the problem at hand. We had to make several tough decisions. We had to make the decision, how are we going to come home? Because we're right in the area where the gravity of the moon is balanced to the gravity in Earth. So we're right in between those two. And if I use my big engine, I can be home in a day and a half. If I go around the moon, that's my other option. It's going to take 4 to 5 days to get back home. So which way am I going to come home? I don't know what happened to that spacecraft, so I better be careful. So I'm going to go around the moon.
Here in Mission Control, we're now looking towards an alternate mission. Swinging around the moon and using the lunar module power systems.
And if I go around the moon, I got a 2-day spacecraft. It's going to take 4 days to 5 days to get back home. So now I got to figure out how to take that 2-day spacecraft, water, oxygen, electrical power, and stretch it out.
And we have a procedure for getting power from the LEM. We'd like you to copy down.
Because the key thing is, once the crew's up in space, you don't want to make a mistake because you're too conservative. You got to wait until you got enough data to make the right decision.
Another cheer in the control room as we head splashdown.
What advice do you have for a young person who's interested in a career in mission control?
Dream, aim high, never surrender. Dream is your goal. What do you think you're best at? And start going after that goal. And what you have to do is you have to have that goal, that dream, so strong that you'll pick up and carry on. It's what I call tenacity. Staying tough, working tough, being tough when it relates to going after your goal. So dream, aim high, never surrender.
That's great advice. Well, thank you so much for talking with me today. It was really nice meeting you.
Will you give me 5?
Yes.
Okay. Thank you. I enjoyed it too.
Dream, aim high, never surrender. That's exactly what the Apollo astronauts did, and so did the many men and women who built the incredible machine that got us to the moon, the mighty Saturn V rocket.
Among its many contributions, Huntsville is where the Saturn V was dreamt up and designed by German rocket scientist Wernher von Braun. It's also where the Saturn V's mighty F1 engines were initially tested, and continues to be a major force in the exploration of space to this day. During my visit to the U.S. Space and Rocket Center, I headed out to Rocket Park to learn more. I'm joined now by Ed Stewart, head archivist at the U.S. Space and Rocket Center, to talk about rocket development in Huntsville. Thanks for being with me today.
My pleasure.
So can you tell me a little bit about the early days of rocket design in the U.S.?
So a lot of American rocket technology is really based on or evolved out of the V2s that were developed in Germany during World War II. The V2 was a liquid-propelled rocket that really was a terrifying invention, and the masterminds of the V2 program was a gentleman named Wernher von Braun, who actually came over to the United States after the end of World War II and became the head of the guided missile development program for the U.S. Army. And then eventually NASA was formed in 1958. He started working on civilian space exploration-based projects. And so von Braun and most of his team transferred over to Marshall Space Flight Center when it was opened in 1960. And that's kind of where you see the beginning of the development of these big space exploring rockets. If you look, for instance, at the Saturn I behind us, the tanks, the skinny tanks that are kind of clustered together around the outside of the first stage, are all stretched out Redstone rocket propellant tanks. And so they took those kind of pre-existing elements, combined them together to produce a 1.5 million pound capable first stage. And that is the first sort of heavy lift or really big rocket developed for the United States. And it was also the first vehicle developed specifically for space exploration as far as like kind of a ground up design.
Building off the successes of the Saturn I, Dr. von Braun's team went to work building the biggest, most powerful rocket the world had ever seen to take us all the way to the moon, the Saturn V. The Saturn V was comprised of 3 stages. The first had 5 massive F1 engines that generated over 7.5 million pounds of thrust at sea level. The second stage, designed to push the rocket through the upper atmosphere, had 5 smaller but even more efficient J2 engines, creating 1.1 million pounds of thrust. Finally, the third stage's single J2 put the Saturn in a temporary parking orbit before firing up again for something called translunar injection. The astronauts tripped to the moon at more than 24,000 miles an hour. While on the way, the crew unpacked the Apollo command and lunar modules through a delicate series of docking maneuvers to prepare for lunar orbit and landing, and finally jettisoned the last stage of the mighty Saturn rocket.
Looking good. Over.
While the Saturn V was a beast of a machine, you might be surprised to learn that today, there's thousands times more computer memory in the smartphone in your pocket than the Saturn V had in its entire enormous structure. But that's not to suggest the Saturn V was dumb. It was anything but, especially for 1960s computer technology. While still at the U.S. Space and Rocket Center, I discovered all about how it worked with the help of docent and former Apollo computer programmer, Luke Talley. So can you tell me a little bit about how the computers on the Saturn V worked?
In the 1960s, what we could put together with a digital machine really couldn't do all the job we needed to guide a missile of the Saturn V. So what we have is a combination of a digital computer and an analog computer. So this is a 26-bit machine, and each of these blocks now has 4,000 words of memory. All right? So there's 16,000 and another 16,000. So when the rocket's flying, both of these are executing the same flight program. And they're comparing the outputs to make sure they're getting the same results. During the flights, we only had a few miscompares ever. Even though it looks kind of old and antique-y like, it worked quite well. So the redundancy is strictly for reliability. Now in the logic itself, we have these circuit boards. Each circuit board has 35 chips on one side, 35 on the other. To give you a feel for yesterday and today, the processor that we built up here with this technology, we would execute about 8,000 calculations a second while it's flying, okay? Your cell phone's doing probably 2.5 million or so calculations a second. So, in order to make this thing fly, you have to do navigation, guidance, and control. The digital computer could do these timed functions, and it did navigation and guidance, but the control function was actually transferred over to this thing, looked like a barrel over here, an analog computer. The analog computer, it flows in, you're multiplying or dividing or whatever you're doing, comparing the data as it comes through, and it just keeps flowing, all right? And it goes right on out, and in real time. Whereas the digital computer, it'll get an interrupt, and it'll go do something, and then it'll go back to doing what it was doing previously. Okay, the computer itself does not have an operating system. So we have a series of signals coming in. When the signal pops up, we go do something. The next signal pops up, we go do something else, all right? And then we also have timed functions. In other words, there's a clock. When this clock comes up, that says to start navigation, guidance, and control. Start it, navigation, guidance, control. So we have clock signals and we have interrupts from the rocket itself.
Thanks for meeting me today, and thanks for telling me all about computers.
You're welcome.
All aircraft rely on a force called thrust to work, which is generally created through applying Newton's third law of motion. For every action, there is an equal and opposite reaction. What does that mean? A good example is rowing a canoe. To move the canoe forward, you push back against the water. This action, pushing back, creates the opposite reaction of moving the canoe forward. In a propulsion system for a rocket, Newton's third law is applied by exploding fuel and a source of oxygen, or oxidizer, in a combustion chamber, which, as every action creates an equal and opposite reaction, this combustion creates a reaction of exhaust, which works as a thrusting force on the system. It's amazing it works. It's more amazing we figured it out. But perhaps the most amazing part of it all? Leaving the Earth was always physically possible, even when humankind believed it was just a fantasy. We just needed the right technology to take advantage of the physics that were already a part of our world. Who knows what other seemingly impossible tasks humankind will make possible in the future?
Speaking of rocket engines, meet the RS-25, formerly the main engine of NASA's space shuttle, and, with some amazing new upgrades, rocket engine of the future, primed to give the Saturn V's F1s a run for their money. These super RS-25 engines will power NASA's Space Launch System, the vehicle that will one day take us back to the moon and even beyond to other planets like Mars. I headed down to NASA's Stennis Space Center in Mississippi to get a first-hand look.
So this is an RS-25 flight engine.
So when was this originally designed, and how has it been updated since then?
It actually flew during this space shuttle program on several space shuttle missions. And so what we're doing now with this engine is we're actually repurposing it from the space shuttle program and actually taking it to making it a little bit smarter and a lot more powerful for the space launch system.
How exactly does a rocket engine work?
So really, what's best for us to do, let's just go upstairs, we'll get real close to parts of the engine. I can point out and talk about how we use liquid hydrogen, liquid oxygen to produce the thrust that we need on these engines. So these areas here, this thing is a high pressure pump. And so there's one just like it on the other side of the engine. This pump is pumping liquid oxygen. On the other side of the engine, the pump is pumping liquid hydrogen. So liquid hydrogen is our fuel, liquid oxygen is our oxidizer. Liquid hydrogen is the second coldest element on Earth. It's minus 423 degrees Fahrenheit. And then liquid oxygen on this side of what we're talking about, it's around minus 300 degrees Fahrenheit. So normally when we think about liquid hydrogen, liquid oxygen coming together, we think about water. And we say, okay, we have hydrogen and oxygen and it comes together and we make water. So how do we make rocket fuel out of water is really the cool question, right? So what we do is we actually take these two elements and we put them under extreme pressure, somewhere between 9,000 and 11,000 pounds of pressure inside the engine. When they come together at that high pressure, they actually hit each other and explode. And that explosion is what we're controlling in the main combustion chamber that comes out of the nozzle. And that explosion coming out of the nozzle is the thrust of this engine, and it's what's making that thrust. So coming out of the nozzle at the bottom is 6,000 degrees Fahrenheit. So you think about instantaneously it goes from these cold elements to plus 6,000 degrees, and that's what's making this, how this engine works as far as producing thrust.
Awesome, thank you so much for your time. It's so awesome, very interesting. I learned so much today.
Looking good. Over.
Alright, let's check in and see what badges we've earned. So for now, we've only got the space race and rocket boosters. 2 down, 4 to go. After reaching the moon, which many consider to be the end of the space race, NASA's human spaceflight program began to change directions and focus on humans staying in space as long as possible.
Following the Skylab program of the 1970s, NASA began its longest-running program to date, the Space Shuttle program. The Space Shuttle was a bold new reimagining of manned space exploration.
Low Earth orbit, an orbit around Earth some 1,200 miles above the planet's surface, was now the goal. And instead of rockets and capsules that were one and done, now reusable winged orbiters would be used.
First launched in 1981, NASA's fleet was comprised of 5 orbiters. All in all, America's space fleet flew 133 successful voyages beyond the Earth, leading to countless scientific advancements.
Without the shuttle, we'd also be without one of the most important scientific devices of the 20th century, the Hubble Space Telescope, a window to the cosmos that's given humankind some incredible first-time peeks into some of the universe's most amazing sights. While at Kennedy, I had an amazing opportunity to learn more about the shuttle program firsthand from one of the brave astronauts who flew as part of the program.
I'm joined now by astronaut Charlie Walker, who actually served as a payload specialist on this shuttle right here behind me, the Space Shuttle Atlantis. So Charlie, tell me a little bit about your experience on this shuttle. Were there any moments that really stood out to you?
Well, launch is always a very memorable experience. Atlantis, during the entire flight, had virtually no electrical or mechanical problems, which was a joy for the crew because we could spend more time getting the useful things done and looking out the window.
So what were some of the most innovative things on the space shuttle?
Innovative. Wings to start with. The earliest manned or piloted spacecraft was a capsule. So wings was a very innovative approach to space travel, not only launching to space, but also returning to Earth. And the wings were only useful on the return to Earth. Another innovation was this Canadian-provided robotic arm. It was an international project, very useful, including on my flight on Atlantis, in which 2 of our crew members did a unique spacewalk to demonstrate construction in space.
So what would you say the training was like to become an astronaut?
To work inside a spacecraft in orbit takes certain necessary skills and personal characteristics. For instance, you had to go through a screening process before you even went into training for the managers to determine that you weren't claustrophobic. You can't be afraid of small spaces in a spacecraft because you can't open the door and get out. And the training then included a lot of course, systems training. Now, I didn't need to learn every system in there. The mission specialists knew how to operate every orbital system with the spacecraft while it's in orbit. The pilots fly it up and fly it back home, and they didn't teach me to do that. That was fine. I was a payload specialist. And then, of course, I had to be very trained up on my particular research, as well as learning to work with my fellow crew members. That took well over a year.
What lessons did we learn from the shuttle program that we're applying to the future of spaceflight?
The Space Shuttle was the first to utilize in that capacity solid propellant first stage booster rockets. We learned lots of lessons from using those booster rockets to launch shuttles into space, and solid rocket boosters are planned and are in development and testing right now for use in the next big NASA launch vehicle, the Space Launch System. And the engines on the Space Shuttle, they're being modified for use on that next big launch system as well. But also learning to train efficiently and effectively crews to work together, that was an important lesson that's being used in the future. The overall efficient technology that was used to control, to do life support onboard Space Shuttle. So all of those things, those are what comes immediately to mind as lessons learned from Space Shuttle for future space activities.
Well, thank you so much for taking the time to talk to me today.
My pleasure.
Thanks to the shuttle program, NASA was able to set its sights, with the help of the rest of the world's space community, on an even greater goal: the world's first long-term home in outer space, the International Space Station. NASA, along with Russia, Japan, the European Space Agency, and Canada, slowly constructed the International Space Station for nearly a decade and a half, from 1998 to 2011, the same year NASA finally ended the shuttle program.
The ISS is a major achievement of human ingenuity and science, and as of today has housed more than 236 people from 18 countries. Truly a space station serving all of humankind.
Thanks to the countless experiments that can only be studied in low Earth orbit, amazing advancements have been made. But none of those experiments could ever have gotten off the ground without the help of an amazing support team in the Rocket City.
We're standing outside the Payload Operations Integration Center at the Marshall Space Flight Center. This is the primary Space Station Science Command Post, and it is here that all of the International Space Station science experiments are coordinated. I'm joined now by Payload Operations Director Christy Robertson. Thank you so much for joining us today.
Thank you, it's good to be here.
So why is this called the Payload Operations Integration Center? What exactly is a payload?
So a payload is the experiment itself. So each experiment that a scientist launches to station is called a payload.
What happens on a typical day in the Payload Operations Integration Center?
7 days a week, 24 hours a day. A typical day begins with a crew wake. Throughout the day, our job here at the POIC is to interface with the crew for their science experiments to ensure that those experiments are executed and be kind of the liaison between them and the payload developer that actually developed the science experiment.
So what do you guys do to help the astronauts in space doing these experiments?
When they have questions or issues, anomalies, they'll call down to POIC, and then we work to get them an answer and a resolution so that they can proceed through their experiment.
What sorts of scientific fields are researched up there?
So we have everything from combustion to rodent research. We also have various life sciences, human research sciences that are done. So many of the astronauts participate in what we call human research experiments, which are those things that evaluate essentially the toll that space takes on a human body.
How does the payload operation team prepare for a scientific expedition?
So we start about 1.5 years out preparing for each expedition. And part of what we do is actually some on-hands training. So we have a center downstairs that I can take you and show you, and we can kind of see some of the on-hands training that we get.
Okay, cool.
One of the things we have for our controllers here to be able to utilize when they're developing procedures as well as getting ready for operations are our hands-on environment. This is the lab that we're currently in. It is a true to life size mock-up of the lab that is on space station, so the U.S. laboratory. So one of the racks that we have there is this one, which is the MSG, which is a microgravity science glove box. So as you can see, the work volume will extend. That just allows the crew members more functionality. So if you want to, you can go ahead and stick your hands in there, see what it would feel like to have a glove on, and see what adjustments you can make. Create a pressure right here for you. So you should see these other gloves kind of fill up around you.
Thank you so much for teaching me all this stuff. I really enjoyed it.
Thank you, and thank you for your time.
Providing for the day-to-day needs and resources of the men and women living and working on the ISS presents constant technical challenges, like recycling precious onboard resources with its water recovery system. The ISS's water recovery system provides clean water to the astronauts by recycling and purifying water waste on board. It does this with the help of the Water Processor Assembly and something called the UPA, or, well, the Urine Processor Assembly, because it recycles, urine. On the ISS, the #1 priority of a #1 is to recycle it. Urine is turned to water with the help of a low-pressure vacuum distillation process. Distillation is the process of heating a mixture of liquids until they become a gas, then condensing the gas back into separate liquids, which successfully removes the clean water from the urine. The water is then moved into the WPA's purification system. The ISS maintains extremely strict purity standards before any recycled water can be consumed by the crew, especially recycled urine.
I am here with Jennifer Pruitt, who is the project manager for the International Space Station Urine Processing Assembly. Why do we recycle urine and sweat for astronauts in space?
When we go somewhere where there isn't water available, like in space,
We need to have those systems. It's crucial for humans to survive. It's very expensive to ship up all the water that we need. So what we have to do is recycle it, which is a much more cost-effective way of giving the astronauts water.
What percentage of the water on the ISS is recycled?
Of all the water that's on Space Station, we have a couple different sources. We have our urine, and that's where a lot of the water comes out of our bodies. There's also some that comes out in our breath and in our sweat when we work out. So if we take all of that together, overall we recycle about 92% of the water, maybe a little bit higher, and we're trying to get as close as we can to that 100%. We have developed our hardware here that we now use on the space station. So I'm going to show you our urine processor that we have right here. This is the same as what is on ISS now with a few tweaks, but we have these clear containers that we use on the ground only. The ones on station are big metal tanks. In space, people would pee, it would fill up, and when it got to a certain point, that would start the process. So it runs in a batch. We have a couple pumps that move the fluid through. These two here, one moves all of our fluid, and it's a peristaltic pump. So it's kind of like your esophagus where it pushes everything through, trying to not use gravity, so it's just that push. We have a purge pump, which is reducing the pressure in the system so that we don't have to boil the water at high a temperature. So to try to save power, we instead bring the pressure down. So we're lowering the pressure so we can boil the water at a lower temperature as well. And we do that in this guy here. This is the distillation assembly where we actually boil the water. He's kind of like a washing machine, is a big drum. The urine goes in, it's boiled, and the steam comes out, and then they're separated from that point on. So the good clean water is what goes on to the water processing, the next cycle, and all of the brine will come back to the beginning, and that will be concentrated until we get enough water out, and then that brine is what's thrown away at the end.
Thank you so much for showing me all of this stuff and explaining to me all these awesome processes.
You are so welcome, and if you ever want to come back and help donate to our Mars mission, you are more than welcome.
While the ISS is an unprecedented, literally out-of-this-world creation, it sometimes requires maintenance and repairs. When something needs to be altered or fixed by an astronaut on the outside of the station, they perform what is known as an extravehicular activity, or EVA, and a very special tool is required.
A spacesuit. Spacesuits are more than just an astronaut's Sunday best. They're highly engineered life support systems in their own right, allowing astronauts to survive and work in the cold vacuum of space. While in Huntsville, I was able to make a stop at the U.S. Space and Rocket Center to learn more about them. Hello, I'm here with Joseph Vick, who is the manager of museum education here at the U.S. Space and Rocket Center in Huntsville. What can you tell me about the history of spacesuits?
Spacesuits originated here on Earth for exploration of the Earth. When we had the need to go and dive, so think of really old school diving suit. Post that, we went from exploring the oceans to exploring the skies. So as astronauts, we begin to explore past our atmospheres. We need even more protection from those lack of pressures. The first of those were used during our Mercury mission, so it was the first manned mission. The suit they had was a very early elementary spacesuit. The second manned mission of NASA was the Gemini suit. They needed to develop a new suit so that they could exit out of the capsule. The first American to do that was Ed White. And then for Apollo, they needed a very much substantial suit that would enable them to not only get out of their vehicle, but walk on a surface that was foreign to us. What it would be like to go into space without a spacesuit. So I need your help. If you could put a little bit of pressure on top, that'll provide our Earth pressure, which is 14.7 pounds per square inch. That's what helps us maintain our shape and function, just like AstroDuck here. I'm going to remove the pressure from this chamber. So it's just as if we're going to have AstroDuck in outer space. So as I remove the pressure, the air pressure within, notice what's happening to our AstroDuck. There's no more pressure to keep AstroDuck as he was shaped here on Earth. So he would expand and expand until eventually pop. So from AstroDuck's perspective, you need a spacesuit. Spacesuits have multi-layers. So each layer has its own importance for protection of the astronaut. So notice the first on the outside piece, it's mostly for protection from flying debris when you're in space. Micrometeorite garment. So if anything were to hit this, it would bounce off and not cause any harm to the astronaut. You have layers, multiple layers of a mylar-like material that provides a thermal protection. Other layers are what are called pressure bladders, which allow the pressure inside of the suit to maintain that pressure. And then you have at the very closest to the skin this ventilation garment, which is the movement of the water over the pipe so that water would flow over the astronaut's skin and body, creating a cooling sensation for the astronaut.
Thank you for all this knowledge. Next time I see you, I'll have my own personal spacesuit.
Oh, great, and I'll catch you on Mars.
Looking good. Over.
The place where all of NASA's iconic launches began is Kennedy Space Center in Cape Canaveral, Florida, America's spaceport. I was lucky enough to get special access to the newly renovated Launch Pad 39B, where Apollo and shuttle missions were once launched, and where they'll soon be joined by the Space Launch System.
I'm here with Tim McDaniel, who is the Launch Pad 39 facility manager. So Tim, can you talk us through getting ready for a launch? What kind of things happen on the pad?
They have to have the electricity hooked up to it, they have to have water hooked up to it, and just like your car, it has to have fuel. On each side of the launch pad, there's liquid hydrogen on one side and there's liquid oxygen on the other side. They bring the fuels together and they fill the rocket. Then once it's fueled, they do all their preparations and getting ready for it. They do all their checkouts, they do all the electrical checkouts, the man checkouts, the systems checkouts. This water tower here, it has several thousand gallons of water in that tank. This tank actually drops every bit of water out of that tank in 1 minute. It flows from that tower and it goes up through the mobile launcher, and it has some big heads that spray water in the direction of the flames where it comes out the bottom of the rocket. And that helps for sound suppression, because as you can imagine, it'd be very, very loud.
What modifications are currently being made to the launch pad for SLS?
They redone the flame trench. They put all new bricks in the flame trench. They also, currently, they're underway, they're making a new liquid hydrogen tank. This liquid hydrogen tank will be the largest in the world. It will be approximately 3 times the size of the current one we have.
Well, thank you so much for meeting with me today.
Thank you.
Time for another badge review. We're adding shuttle and life systems to our collection. Home stretch now, guys. Just 2 more to go. And to keep us moving, let's kick it back to Kaylee and Chandel, who are learning about the future of the United States manned space exploration program.
Ever since the shuttle program ended in 2011, NASA has had no fleet to send astronauts to the International Space Station. While private companies like SpaceX, Boeing, and Northrop Grumman have learned to launch satellites and ISS supplies at launch sites around the country, and NASA has launched rovers like Curiosity to Mars, the agency has relied on the Russian space program and its Soyuz rockets to deliver astronauts to the space station.
But NASA won't be without a space vehicle for much longer. The Space Launch System, NASA's super heavy lift expendable launch vehicle that's ushering in a new direction for NASA's space fleet in the tradition of the Saturn V, will be the most powerful rocket in existence, with thrust capacities even greater than its moon-delivering ancestor, and with crew on board the Orion capsule up top, NASA will once again be able to send astronauts distances beyond low Earth orbit.
I'm here with Scott Wilson, NASA Orion Productions Operation Manager, and Jules Schneider, Lockheed Martin Orion Productions Operation Manager. Thank you so much for joining with me today.
Well, thank you very much for having us.
Thank you.
Can you give me a brief history of the Orion program?
After the shuttle program, we were looking to decide where do we go next, right? So for many years, we've gone to what we call low Earth orbit, which is about 250 miles above the planet. and that's where the ISS is. And we really wanted to begin exploring deep space, which is getting us back to the moon and Mars and beyond. So we did a lot of studies trying to figure out what would our spacecraft look like, and eventually that led to Orion, and that's what we're building today.
And why did we go with the capsule design again?
Well, in the early studies, we looked at should it have wings like a shuttle, should it be a capsule, or variants of those. And the winged idea is really good for shuttle when you go to low Earth orbit and you're returning to the planet. You use those wings in the last parts of re-entry when you're back in the atmosphere. But from a deep space exploration, it's a lot of weight that you take that you don't really use for your whole mission. Another piece was safety driven. So a capsule, by its design, if you lose the ability to control the spaceship, it's still going to land. It lands like a badminton birdie. It might not land where you want it to, but it lands and the crew is safe. And so it has some safety aspects to it that's important to us. So those are the two reasons it looks like it does today.
Jules, can you describe some of the big advances that set Orion apart from its predecessors?
So let's go all the way back to the Apollo program, because that was the last capsule program we had. As you can imagine, from the 1960s to now, advances in just technology on many different fronts, from computers or computing capabilities and speeds, to materials, to advanced manufacturing processes like 3D printing. So almost in every category that it takes to design and build a spacecraft like Orion, there have been huge advances.
You'll notice the solar arrays here, right? So Shuttle and Apollo used commodities on board to generate electricity, and that meant you could only generate it for a limited amount of time until you run out of those commodities. With the solar arrays now, we can generate electricity indefinitely when you're in space. That's kind of one simple example.
What are the biggest challenges of a long space trip, and how is Orion meeting them?
If you're in low Earth orbit at the space station, for instance, you can return home in 90 minutes or so. You may not come down exactly where you want to, but you can get home pretty quickly. If you're going to the moon, it could be days until you return, and if you're going to Mars, it could be years. So the further you move away from the planet, the more redundancy and things you build into your spacecraft.
Jules, what are the launch plans for Orion and SLS? When will we be aiming for Mars?
Well, the next orbital test flight is called Exploration Mission 1. We actually are building the Orion for Exploration Mission 1 right now. It's almost finished. And the plan for it is to launch late next year. Maybe early the following year. Beyond that, we have Exploration Mission 2, which we're also building here at the Kennedy Space Center as we speak. I believe that's in the 2022-23 time frame, and that'll be the first crewed mission, so we will have people, astronauts, on board EM2. And then Mars is probably the mid-2030s. And prior to Mars, NASA's plans are to put the Gateway, which is a spacecraft orbiting the moon. And so before we go to Mars, our plan will be to go to the moon multiple times and then use that as a launching pad for a Mars mission.
Wow, well, thank you both very much for meeting with me today.
No, thank you very much for your time. I appreciate it.
It's nice talking to you.
Very nice.
While Kaylee was learning about the mission of the Orion program at Kennedy, Chandel was at Johnson Space Center in Houston to learn even more about the Orion capsule.
We are in Building 9 at Johnson Space Center. Building 9 is home to NASA astronaut training and space vehicle mock-up facilities. Behind me is a full-scale mock-up of the Orion Crew Exploration Vehicle, and I'm joined here by Orion engineer Najoud Moranci. Thank you for being here with us today.
You're welcome. Thanks for coming.
So I understand that the Orion will sit on top of the SLS rocket. What can you tell me about its design?
So one of the key parts of the design of Orion, we can abort at any time during ascent, and once we get out in space, Orion can always turn around and come home as well. So that's a really fundamental part of our design, was making sure the crew is safe throughout the whole mission.
And how do you keep the astronauts safe in here?
So there's a lot of ways we do it. So first off, there's redundancy. So everything has a backup to it. There's multiple tanks of water, there's extra computers. So no matter what happens, we can always actually come home on the backup system that's on board. One of the fundamental parts of spaceflight is keeping the crew safe by having redundancy and then having lots of our contingencies planned out ahead of time to be able to respond to those emergencies.
What will it be like for astronauts to live in Orion while in space?
So it's kind of like a camping trip. They'll be inside, we can have 4 of them in there, and they'll have to bring all of their food and clothing, and they've got a shower and waste management system. It's actually in the floor in there, and they bring sleeping bags. So they'll be doing experiments throughout the day, they'll be monitoring the ship's progress, but then they have to do lots of exercise so we can keep their musculoskeletal system from degrading. They'll be eating meals, they'll be having leisure time.
And what are your responsibilities as an Orion engineer?
So I'm actually the mission analysis lead for the program, and my team are actually designing the missions to the moon and home again. So we have to make sure that when we're done building Orion, we can actually accomplish the missions, and the mission designs are something Orion can fly.
Can we take a closer look?
You bet. Let's go inside.
Awesome.
So inside here, this is the Orion medium fidelity mock-up, and this is here to train the astronauts as well as allow the engineers to figure out what the design looks like on the inside so we can make sure everything's going in and will fit when the space vehicle actually flies.
Well, I see the controls in there. So could you tell me how they control this vehicle?
So the crew will actually fly it, but most of the vehicle flight is automated. So we'll have software that's on board controlling it. There's thrusters and engines that are in the service module that would be beneath where we are right now, and that actually flies the spaceship with the ground control monitoring and then the astronauts providing oversight over what's going on.
Thank you so much for talking with me today.
You're welcome. Thanks for coming.
I really enjoyed it.
In order for the SLS to make it to Mars and beyond, we're going to need a lot of power. The RS-25 engines are more than up to the task. But before the engines are ready to be used in any real-life situations, they have to be tested rigorously and for years to ensure that they'll perform as required. To learn more about this all-important testing process, I got an opportunity to speak to one of the engineers working tirelessly to get these engines ready for launch.
We are standing near test stands at Stennis Space Center in Hancock County, Mississippi. I'm now joined by Tommy Carroll, a NASA engineer. So why don't we test the physical engine instead of just using a computer?
We use computer modeling for a lot of different things. We use it in design. We use it to check out clearances of hardware. We also use them to model what should be happening inside of the engine. And when we run that engine, the physical engine, and actually see it, we're baselining our models, but we're also looking at some of the variables that we're going to see. And that's why we test.
What is the engine test today going to tell us about?
We're going to be looking at a green run controller. That means a brand new controller, the computer that tells the engine what it needs to do.
So what's the next step from here, and how many more steps are there going to be until the engine's ready for launch?
So this engine that we're testing today is a development engine, and that just means that we use it for testing parts, not for testing the whole rocket engine. But the very next engine that we're going to test is a flight engine that will fly in space. So we'll take that engine after we test it, we'll ship it from here to another facility called the Michoud Assembly Facility. We'll install it on the rocket along with 3 other engines, so have a total of 4 rocket engines on that. We'll take that, that's called the stage, we'll bring that here, we'll mount it on that test stand, and from there we'll test it again. And once we've done that test, we'll put it on a barge again called the Pegasus, and we'll ship that barge from here down to Florida. And they'll put the whole rocket together there and then roll it out to the launch pad.
Awesome, great information. I can't wait to see this test.
It's going to be good.
Oh yeah.
Yeah.
To operate engines like the RS-25, you need a lot of fuel and a pretty big gas tank.
We're at the liquid hydrogen test stand at NASA's Marshall Space Flight Center with NASA's structural engineers Robert Bobo and Sam Stevens. Thank you for talking to me, guys.
It's a pleasure to be here.
Thank you.
Robert, can you give me an overview of the systems and the components of the SLS?
Sure, and I'll set it with reference to the test article that's behind us here. The test article that you see behind us is the liquid hydrogen tank for our new SLS launch vehicle. The hydrogen tank is our fuel tank, if you will, for the entire vehicle. The liquid engines on this vehicle run on liquid hydrogen and liquid oxygen. Those are the propellants that we use to produce the thrust. In addition to that, we have a solid rocket booster attached to each side of this liquid hydrogen tank for added thrust to get through the Earth's atmosphere. As we go up the stack, if you will, there's an inner tank that sits on top of this. Above the inner tank is where the LOX tank, or the liquid oxygen tank, rides. Then we adapt to our second stage. Then we adapt to the Orion, which includes a service module, a crew module, and a launch abort system.
Sam, what are structural tests and why do you do them?
Well, the structural tests are very important to us. You've got these engines underneath and beside that are pulling, winds, pushing, all sorts of different forces that it has to be able to withstand. So we do structural testing. We put all these forces into the rocket to make sure that it can withstand those and the vehicle's safe to fly.
I know that this rocket is designed to take us back to the moon. What are the similarities between the SLS and the Saturn V?
Some of the primary similarities are the fact that we use liquid propellants through the rocket engines to generate the thrust to get to the moon and complete the mission. We also have to do it in stages. One stage or one set of engines doesn't get us all the way there. And a little difference with SLS is we have the solid strap to each side for the first phase of the mission.
So why does America need this rocket to go to the moon?
There are other nations, other private companies who are building rockets, but none of them have the payload capacity that we need to launch an Orion carrying multiple astronauts or very large payloads. We need an SLS with all of its launch capability to get all those things to the moon. Once we get to the moon, we can learn how to work with these large components, and from there, we can eventually move on to Mars.
I know that you guys said that the rocket was going to be big, but how much bigger will it be compared to what's behind us right now?
So what you're looking at behind me, the test article here, is about 150 feet tall. The Space Launch System itself, add another 100 feet to that, about 320 feet tall.
Wow. Well, thank you guys for talking to me today. I really appreciated it.
Thank you. It's been a pleasure.
If you're going to get something the size of NASA's Future Space Launch System, or SLS, off the ground, you need more than just brawn. You need brains, computer brains, the best science has to offer. The SLS's computers work using the same basic principles as the computer or smartphone you interact with in your daily life. In order to function, computers need programming. Programming is built by humans by writing lines of computer code, a language spoken by computers which is then input directly into the computer. With this code, computers can be programmed to do actions automatically, like turn on and off certain circuits or valves on a rocket at specific times. This allows human controllers the ability to manage hundreds of delicate operations on the SLS that would be impossible without a computer. The Space Launch System has both brawn and brains. And as NASA's future vehicle for sending humans into space and beyond, it'll be one of the smartest rockets ever when it takes flight.
I really wanted to see how engineers are testing the computer hardware that's responsible for operating SLS launch systems.
And now we're here at the SLS Systems Integration Lab. Here, engineers install different components into this system unit mock-up to try to see how different things work together. I am here with Hannah Hopkins, SLS software engineer, and Alex Matris, aerospace engineer. Can you explain to me the systems on this SLS?
Well, there's a lot of avionics systems on board, and avionics are just the computers which operate all of the systems that fly the rocket. One of the systems is the flight computers. It's what's doing all the controls, it's the autopilot system, and it's checking all of the sensors and everything else to make sure that everything's still working well for flight.
There's 3 flight computers, and they're basically the brain of the operations. And if one of them fails, it's okay. They vote it off the island and we keep going. But if 2 of them fails, things get a little risky. So we definitely need these. These are crucial to flight.
There's other instruments such as a redundant inertial navigation unit, which is a fancy term, but all it's doing is just figuring out where we are when we're in space. There's other systems for like hydraulics and steering the vehicle so that you can steer it to get it to wherever you need it to go to.
We also have the engine controller over here. The engine controller basically controls the mixture ratio between the liquid oxygen and the liquid hydrogen tanks, and so it controls the thrust of where it goes. And it also takes all of the sensors from the engines, and it can look at, is this engine failing us, or is this engine okay? Is it doing what it's supposed to do? So you can kind of think of the systems of the SLS as kind of the central nervous system of the rocket, especially the avionics components in here.
How do you test SLS systems and software in here?
We test all of the hardware and software in here with a simulation called Artemis. And so basically what we do is we write code to simulate all of the different models on SLS and all of the different components. Something cool with that we can do is we can say, what if one of the engines fail? Or what if all the engines fail? Or what if the flight computer quits on us, or something like that? And we can see how the rocket is going to react so we can better prepare to how to handle that on launch day. In fact, we've actually run about 15,000 simulations in here, and so we've launched the rocket 15,000 times.
We present the flight computer any number of scenarios to make sure that it can detect all the kinds of different faults and still keep flying safely. You can't do all of these with a real test flight.
Yeah, and so that's one of the big differences between now and the Apollo days, is that they didn't have that software to be able to test it as much as we have.
What are some of the things that you've learned from the testing that you've done here?
Well, our job is to bring a lot of different pieces together all in one place. There's a lot of different people making a lot of different parts of this vehicle. So we'll find issues where two things may not talk together the way we thought they would. We can figure that out, fix it, and test the solution to it right here in our lab, and then go make that happen in the real hardware.
Thank you guys so much for telling me about all the awesome stuff you have going on here.
Yeah, of course. No problem. It was our pleasure.
Is that it? I think we got them all. Let's check. And that's future exploration and space computer controls. We did it. Great work, team.
Yes! But we really couldn't have done it without your help.
That's right. Every single one of you viewers out there should now consider yourselves members of the STEM Brigade, just like us.
Exactly. Together, we all learned about the science and history behind human spaceflight.
And the endless possibilities in the future of our travels away from the big blue marble we call Earth.
Thanks for joining us on our out-of-this-world journey. And now...
STEM Brigade, over and out.
We are advancing today's space communication and navigation services and technologies to meet tomorrow's challenges. SCAN is committed to ensuring vital space communications through a network of complex ground stations and tracking data relay satellites. Together, these systems enable continuous communications and global coverage for space programs. Every space mission delivers terabytes of vital information for the process of scientific discovery. Our extensible and expandable communication and navigation infrastructure provides a resilient space framework that can meet the growing requirements of our users. We develop, operate, manage, and engineer pioneering solutions. Transformational technologies in satellite communications are underway. Cognitive systems will enable autonomous satellite networks, and optical communications will increase our ability to send and receive data to the vastness of space. We are developing these and other technologies to advance explorations of Earth, the lunar region, and beyond. Spectrum, the medium that enables communications and navigation. Through coordination, we ensure efficient use of this limited resource. We work with P&T partners to provide space missions accurate position and timing information. The most exciting part of this journey lies ahead, collaborating with commercial industry on major advancements in space communications. Our next generation of visionaries are creating a bright future, enabling Artemis lunar communications and a pathway to Mars. NASA Space Communications and Navigation. SCAN. Exploration enabled.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
Feeling the constant pull to the Earth? We all are. It's gravity, and it's a part of every single thing we do, including our science. But what if we're 250 miles above Earth, aboard the International Space Station, a laboratory like no other that offers something we can't get on our home planet?
My name is Dr. Serena Anand-Chancellor, NASA astronaut. I recently flew to the International Space Station aboard Expedition 56 and 57. My relationship with microgravity is that I got to live in microgravity for 197 days when I was on orbit. So many people ask, what is microgravity? Why do you float on board the International Space Station? Gravity acts upon all objects. We're never truly in zero gravity on board the space station. But because the space station is traveling so fast around the surface of the Earth, we're actually in a constant free fall. And that's why everything and everybody appears to float on board the space station.
We are experiencing the Earth's gravity. In fact, we're actually experiencing about 90% of what you all experience on the surface of the Earth. The difference is we're just moving so fast that as we fall, we actually fall around the Earth, and that defines orbit. So microgravity means we're not, it's not the absence of mass, which of course creates gravity, but all the objects together are in the same gravitational field and all falling together. So yes, it is a lot of fun. Floating around, of course, is one of the exciting parts of being up here on board and being an astronaut, but even more importantly, it lends itself to all the amazing experiments that we can do on board that take advantage of that microgravity environment to do things that we can't do on Earth, but that can benefit life back on Earth.
The important thing is it's so different than what we have here on the ground, where everything is pulled by the Earth at what we call one force of gravity. And what that does is it allows you to see the small forces, the small processes, the small effects of what goes on in life cell development or technical processes like combustion or fluid flow. And it helps you understand things that you may not have fully understood on Earth, where you see something happening, something assembling or disassembling, or the shape of something now going into 3 dimensions. And you learn, that's really what was driving this thing on Earth that we didn't really understand.
On Earth, gravity is affecting all research we do, and sometimes that can get in the way. Studying things in different environments can give a better picture of how they work, from diseases to fires and even things that make up products like milk or shampoo.
One of the main things we perform on the ISS is science. In fact, probably 70 to 80% of our day is performing scientific experiments.
The International Space Station is a great place to do research for several perspectives. One of those is it's a big, huge satellite orbiting the Earth. So if you have an instrument that wants to look at the Earth or look out at space, we provide the power, we provide the data, the platform for it. You don't have to go do your own new satellite. The outside of the ISS is also a very extreme environment, and sometimes you learn things by exposing your hardware, your polymers or whatever, to a different environment. You'll see something happen different than what is on the Earth. But probably one of the most pervasive uses of the ISS is just the microgravity environment, the things that we do inside the ISS. To be able to do your experiment in space without gravity, which we've all lived with forever here on the ground, which we live with every day, and we don't even realize how it governs so many things that happen around us. If you take gravity away, now some of the small phenomena, some of the small processes and forces start to come out, and you can see them, and you can see the behaviors of your experiment happening differently in space and in microgravity than you would on the ground.
It takes a lot of people to make all of that microgravity science happen. 4,000 scientists, companies, and students from over 100 countries have sent more than 2,700 experiments to the orbiting laboratory. Over the past 20 years, these studies have unlocked new discoveries and even kicked off hundreds of new microgravity experiments.
We're studying the physiology of how blood flow and our
the fluids in our body shift as a result of microgravity.
Yesterday, I spent some time setting up a veggie experiment. We'll actually be growing Mizuna lettuce up here.
Drew and I actually have been helping start a new experiment called the Cold Atom Lab, which will create one of the coldest places in the universe right here on the space station, almost at absolute zero.
But who are these scientists? And how do they get their research to the space station? This season, we'll take you behind the scenes of the years of preparing an experiment for space. You'll see it launch off the planet and splash back down in the ocean, and hear what it's like to hand off your research to the astronauts who serve as the eyes and hands of the scientists aboard the International Space Station.
This is our first project that is going up to the station, and our first project working with anyone involved in the space program. So it's a very exciting time for us. It'll be interesting to see how all of our planning is played out when someone else has the experiment in their hands.
These two tanks are from the Sphere's slosh experiment, which we've been working on up here.
Microgravity has a lot to teach us. Take these containers. The green liquid inside is showing us how fuel swirls around in a tank while it moves through space. What we learn could help us design safer, more efficient spacecraft. At any given time, we are conducting close to 300 different experiments aboard the International Space Station. Research like this is preparing us for the future of space exploration.
That's cool.
We really can't mimic the environment on the space station anywhere on this planet. And it's what makes it such a special place, and why scientists from many universities, several companies, like to send their science up, because once you remove gravity, many things act differently.
This season, we're exploring why we send science to space and what it takes to get it there. Spoiler alert, you don't have to be a rocket scientist to conduct research in microgravity.
So this is our first project that is going up to the station, and our first project working with anyone involved in the space program. So it's a very exciting time for us. The transition from what am I going to do with my life in the middle of graduate school to here I am sitting in Houston getting ready for our launch. I can't hardly believe that it's actually happening.
Meet Elaine, one of the co-founders of Tympanogen, a medical device startup based in Virginia. Her company is developing a gel patch that can serve as a replacement for eardrum repair surgery. That could have huge benefits here on Earth, but launch that gel to space, and the opportunities for use grow even more. First, we have to back up a few steps. Putting your life's work on top of a rocket may seem like a daunting task, but there's a system in place to help scientists who know nothing about spaceflight get their research into orbit. You see, NASA and its international partners aren't the only source of science aboard the space station. The ISS U.S. National Laboratory creates pathways to space for companies, universities, and even young students. If you're starting a journey into the unknown, it helps to have an expert at your side to navigate the way. The National Lab connects researchers with implementation partners who provide resources and guidance for taking an experiment from Earth to microgravity. Elaine and her team are working with nanoracks.
They have the plate reader on the space station that's going to be used for our project, and they're coordinating the launch and getting all the materials together for us. We're glad that we're working with them because we're glad that somebody has done this before and can help us along with the process.
7,643.
The project that we're sending to the space station is looking at how hydrogels behave in microgravity conditions, and we're specifically looking at how the structure changes and how drug release profiles change in the absence of gravity.
My name is Paris Du. I'm a co-founder and co-inventor of this technology, and I've been with Tympanogen since day zero. Hydrogels are a very important materials. They are high volume water that can very well mimic the extracellular matrix of our body. So we really thought that answering this question can really help the scientific community.
Confused? Don't worry, we've got you covered. Think of hydrogels like a scoop of gelatin. Not quite a liquid, not quite a solid, definitely made up of mostly water. We can use hydrogels to cover wounds and even deliver antibiotics to promote healing. For that reason, hydrogels are being studied for use for things like wound care for soldiers on battlefields.
If you are far away from a hospital or a clinic and you can't get good medical care right away, and that soldier has a wound, could you apply that hydrogel directly to the wound site and begin to treat any infection that might be coming on? What about in space, though? What if we are far away from Earth's surface, on our way towards Mars, and we also have another wound on an arm or a leg, and we need a better way to treat that wound and make sure it doesn't become infected? So Tympanogen, the hydrogel itself, is a great example of a dual-purpose technology. It's something we can use not only on the Earth, but up in space.
This research could provide previously unknown foundations for future hydrogel studies. It's a great example of how microgravity can offer new insights into systems we've already explored on Earth.
The data that we're collecting is so basic science that it's hard to find those sorts of projects at this stage. As a researcher, that's really exciting for us as well. And it's in space.
And when it gets to space, it goes into the hands of astronauts who will run the experiment in orbit. Just like training for launch, landing, and spacewalks, crew members participate in hours of scientific training to prepare them for running many of the hundreds of experiments that are ongoing aboard the space station. Ready to go to class with an astronaut? We'll take you along.
Well, a lot had changed in 11 years since he was up there. There was a new experiment, so he hadn't seen that either. They tell us, you know, hey, this is a lot easier if you just go upside down. You know, you're going to be in microgravity and this will work differently.
Hi, I'm Terry Virts, and I want to talk about floating in space. One of the first things that you need to realize when you get into space is that even though you feel like you're falling, you're not. You can let go and you float. It's not a problem. It's something you really have to train your brain to think about. Another thing that you need to learn when you first get into space is how little force is required to move you. And another cool thing is you could be on the ceiling. It makes it very easy when you're working. You have to get some work done up here, you just go up on the ceiling and get your work done.
Our team of scientists is busy getting their experiment ready for launch. At the same time, NASA is preparing the space scientists who will operate the experiment aboard the International Space Station.
So as astronauts on board the space station, we are the hands and eyes of the researcher. They are telling us how best to do the science, but it's up to us to make sure that science runs correctly.
Astronauts train all over the world, including at NASA's Johnson Space Center in Houston, Texas. Here, they learn not just how to live in space, but also how to conduct science in microgravity.
So many folks ask, how much training did you do before launching to the space station? And the answer is many years. So we train in a lot of big areas. Number one is systems on board the ISS, robotics, how to do spacewalks, and actually science itself. Now, we don't learn about a lot of the science experiments we're doing until we get up there, but what they are teaching us is scientific techniques.
The techniques astronauts learn range from using tools like pipettes and microscopes in microgravity to operating scientific hardware aboard the space station. For example, we study combustion aboard the station because it behaves differently in microgravity. You wouldn't want fire to get free inside your home in space, though, so we've created special facilities to contain it. If it looks complicated, it's because it is. And it's just one of the pieces of equipment astronauts must master before they go to the space station.
Hi, I'm Tracy Neff, and this is Sharon Ranke, and we're in PDL2 right now, and we're down here at JSC to do the Fluids and Combustion Facility training for the Combustion Integrated Rack and the Fluids Integrated Rack.
So basically, PDL2 is a mock-up of the US lab. Since 2008, we've been coming down and training all of the crew members who will do payloads on the space station. We've been training cosmonauts as well.
How many crew do you think you've trained at this point?
Probably 50. Probably over 50 crew members we've trained.
Today, Tracy and Sharon are back at work with a former student, NASA astronaut Mike Fink. This isn't Mike's first rodeo with the station, or this equipment for that matter.
So back in 2008 and 2009, we were aboard the International Space Station when a space shuttle, STS-126, Chris Ferguson and crew, dropped off a whole big bunch of packages. And we carefully and slowly put it all together. But when it was all done, we had a brand new, ready, fresh out of the box combustion integration rack. And since then, our friends at Glenn Research Center here at NASA, we've been able to get some fantastic science about how things burn in space. Without gravity, without convection, things burn. And by understanding that better, we were able to make more fuel-efficient engines and things here on planet Earth, helping save our energy.
So you can see it in the video. All the hoses are within the ring, and so they all fit in nicely, so they shouldn't interfere with us.
Sounds great and looks great. Thank you.
Well, a lot had changed in 11 years since he was up there. So he did get most of the information again, and there was a new experiment, so he hadn't seen that either. He did great. He's a quick learner. It's great to work with, very methodical, and good humor, which is always, we like to have fun when we're training.
But the lab camera will be showing,
we have
and
the camera.
I will be like looking, and I'm gonna go slowly, and that would be your chance to say no.
Yes. We are watching you, yes, and help you whenever we can.
This isn't the last time Tracy and Sharon will work with Mike. When he launches to the station and works on combustion projects in space, they'll watch over his shoulder through a camera broadcasting to Glenn Research Center in Cleveland, Ohio.
Christina, this is Sharon with an answer to your question. So they do want you to go ahead and install the cable tie. Copy all. Thanks for hunting that down for me. Anytime.
Being able to operate and maintain the space station while conducting crucial research could get overwhelming. Luckily, astronauts have strong support teams on the ground and often develop personal connections to the research.
I was so impressed at the different things we'd be working on, cancer or Parkinson's or even Alzheimer's disease. So as a physician, these meant a lot to me. These personally were very important experiments that we needed to do. But in all honesty, the entire crew, not just myself as the physician, were excited about working on these experiments. You get a little nervous at first as you begin to pipette or even utilize a microscope, which I hadn't used in years. But you quickly learn because you realize how important it is to the science, and the investigators and scientists running you through all these experiments were fantastic and just walked us through every step of the way.
Yeah, just keep us posted, but Drew and I are ready to continue up. Good working with you guys today, and I'll see you soon.
We got here on a Thursday, and it's currently Sunday. We put in a big day yesterday filling up these wells with gel solution and getting ready for handover at 7:30 a.m. on Monday, ahead of launch on Tuesday afternoon.
From space, we see deep into the heart and veins of our ever-changing planet. Pictures of Earth are worth more than 1,000 words. They are the blueprint for our future. To unlock the full potential of space's unique vantage point, we've created powerful tools. Tools that gather valuable data. Data that enables farmers to efficiently manage water and fertilizer for stronger food yields. Data that scientists use to monitor ticks and mosquitoes that carry harmful diseases. Data that first responders use to find the fastest routes to save lives. That's only a glimpse of what we can do today. In the future, when combined with AI and powerful computing, a broader range of space data would generate infinite solutions for Canadians. Imagine a future where we can use space data to better understand and predict the impacts of climate change, like rising sea levels, extreme weather, wildfire risk, and flooding. Measure the health of our forests and create predictive maps of pest damage and burn extent. produce real-time dynamic navigation routes to protect whales and other endangered species, ensure security and sovereignty in Canada's vast Arctic. Tomorrow's challenges require investing in innovative solutions today. Earth observation is key to securing economic opportunities and improving the lives of Canadians. Together, we can define Canada's future.
This is a story about heat. Heat in our atmosphere, our oceans, and land. When you think about it, events like droughts, hurricanes, and fires, all of those are just different ways we see heat expressed throughout the Earth system. You've probably been bombarded with a lot of intense headlines in 2020. Hottest temperature recorded here, largest wildfires there. It's been a lot to take in. My name is Leslie Ott, and I'm a research meteorologist at NASA's Goddard Space Flight Center. So the reality is the stage was set many years ago for these events. Over the last century, human activities have increased the concentration of greenhouse gases in our atmosphere. These gases act like a blanket, trapping heat and leading to overall warming of the planet. Many of these gases remain in the atmosphere for a long time, meaning that we'll be feeling the consequences of this trapped heat for many years to come. Which unfortunately means next year is probably going to bring a lot of the same kinds of stories that we saw in 2020. But taking a look at all the different ways our planet responds to the variations in movement of heat can help us better prepare for the future. Maybe one of the most obvious ways that we saw heat this year was through fire. I know the Australian bushfires were big news last January, and when you think about it, years of prolonged hot temperatures and drought really set the stage for these fires to be more likely and more severe. With drought and heat waves, we typically see an increase in the availability of dry fuels, which leads to more powerful fires. So when you have multiple years of intense heat, it's not surprising to have significant fire events like we saw in Australia. These fires were so extreme that we saw smoke injected as high as 18 miles above the surface. That's really important because when smoke is injected that high, it can have the same type of effect as a volcano, having these very, very broad impacts across whole hemispheres of the planet. At NASA, we use computer models like the Goddard Earth Observing System to help us study how aerosols and particulate matter move through the atmosphere. So we take these models, we input real-world observations and data to track fire emissions to help understand how they're forming, where they're going, and how much of an impact they'll have on you and me. In California, heat waves have increased fire risk, and as a result, we saw a lot of synchronized fire activity. That is, many dangerous wildfires burning at the same time. And unfortunately, these types of huge fire events are becoming more and more common across the western United States. And that's a big problem. This year, Siberia also had a remarkable and active fire season. What we saw was that temperatures in the region were much higher than normal for this time of year. In fact, the temperatures above the Arctic Circle broke records in many of the same regions where the fires were burning actively. In the Arctic and boreal forest ecosystems, heat waves can exacerbate fires. And in the Arctic, you also have to factor in permafrost, which is soil that's frozen for long periods of time, and that can make the impact of fires in high latitudes even more complex. When severe fires burn in areas with permafrost, we lose this important insulating organic soil layer, which accelerates thawing, and it's potentially releasing carbon that's been stored in the soil for hundreds and in some cases even thousands of years. And you sometimes see these zombie fires, which happen when wildfires burn deep into peatlands or smolder in forests under snowfall. If that temperature doesn't get cold enough to extinguish the fire, they can continue to burn over the winter, even long after the visible fire's been extinguished at the surface. So come spring, they reemerge and they continue to burn back on the surface again. Studying what happens in the Arctic is really important because it's warming about 3 times faster than the rest of the planet. And all those aerosols and the carbon that come out of the Arctic don't necessarily stay there. They affect the heating and air pollution in much larger regions of the planet. Another part of the planet affected by heat, of course, is ice. Land ice in the form of ice sheets and glaciers where we've seen significant melt in recent decades, and frozen ocean water, or sea ice. This year, the Arctic sea ice minimum almost reached a new record low. It was second only to 2012's extent, which was an anomalously low year in part due to unusual weather conditions. Sea ice shrinks and grows with the seasons. After reaching an annual minimum extent in September, Arctic sea ice begins to grow again as sea temperatures cool off for the winter. This year, Arctic sea ice had an unusually slow start to the regrowth period. In particular, the Laptev Sea, which is sometimes called a sea ice nursery because much of the Arctic sea ice initially forms there, was too warm for meaningful sea ice growth until much later in the season than usual. Oceans absorb heat from the sun, and our atmosphere prevents this heat from escaping back to space. The movement of this heat is one of the primary drivers of circulation and global weather patterns. We can measure the temperature of the ocean, and what we saw this year was unusually high surface temperatures across the Atlantic. The warm moisture that comes off the ocean acts as fuel to storms. So as this layer of the ocean gets even warmer, we're seeing that storms are becoming more and more intense over time. In fact, 2020 sea surface temperature contributed to an exceptional year in terms of Atlantic hurricanes. We saw 30 named storms, a new record, and 12 of these storms made landfall in the US. What's really interesting is that many of these storms intensified really rapidly. Not only are storms intensifying more quickly, but what we're seeing is that they're stalling near coastal regions more often, which is devastating in terms of floods and storm surge. While we're not 100% sure what is causing these storms to stall, it may have to do with climate patterns shifting in response to rising global temperatures. It's always really tough for a scientist to say any particular fire or any particular event was because of climate change. But we're getting to a point where we're starting to see season after season of record-breaking wildfire, season after season of really intense storms, that it becomes much easier to understand that this is likely the result of long-term climate change. In general, more heat means more energy in the Earth system. So while 2020 was a significant year, it's important to know that this probably wasn't an anomaly of a year. We're likely to experience many similar years as the Earth's climate gets warmer. So while we saw a small dip in emissions this year due to COVID shutdowns, it was pretty short-lived. The vast majority of our greenhouse gas emissions come from things like electricity generation, which were less affected by the shutdowns than emissions from cars and airplanes. But we know that human activities have a powerful impact on our environment. Long-term strategies to curb human-induced climate change would have to focus on implementing cleaner technologies so we can reduce emissions without affecting people's daily lives. So while this is a story about heat, this is also a story about connections. Nothing on our planet happens in a vacuum, and our actions today impact our tomorrow. The choices we make now can make the difference between continued increases in greenhouse gas emissions and 2020 being the year that they peaked.
Did you know that if you were born after 2000, during your entire life there has been someone living in space? That's thanks to the International Space Station, which celebrated its 20th anniversary of continuous human habitation in 2020. You've probably heard a lot about the incredible science that happens on board the station, but the outside is actually prime real estate for all kinds of experiments and technology development too.
The International Space Station is a great platform to demonstrate service and technology because it provides power, data, there's robotics in space.
With Tech on Deck, we'll be talking about some key experiments that have taken place outside in the harsh environment of space, which will help us advance human exploration.
Nexus is NASA's Exploration and In-Space Services Project Division at the Goddard Space Flight Center. The goal of the division is to usher in a new era of more sustainable, affordable, and resilient spaceflight, both near the Earth, around the Moon, and deep into the solar system. Many members of the Nexus team started off with the Hubble telescope servicing missions. We've taken that technology, applied that to robotic servicing.
From robotic refueling missions that will help spacecraft live longer and journey farther to autonomous navigation systems, NASA's Exploration and In-Space Services Division has taken advantage of the wonderful opportunity station offers to test new technologies. As we look to exploring our solar system and beyond, and establishing a sustained human presence in space beyond low Earth orbit, many of these technologies will play a key role.
We use the robots on Space Station to demonstrate the technologies needed to enable satellite servicing in the future. We've also used the robots on Space Station to do some of the more repetitive tasks or the dangerous tasks that astronauts shouldn't be doing, like going outside the space station to try to look for ammonia leaks. Robots are very good at moving fine, delicate positions, moving back and forth, doing those sorts of tasks that would be challenging for humans to do.
In order to live in space, astronauts will first need to reach their far-out destinations like Mars. This will require refueling and replenishment of oxygen supplies, things the robotic refueling missions worked to demonstrate on station. They will also need to be able to construct, maintain, and repair their habitats, as well as adapt to unforeseen circumstances.
Because we're in space in low Earth orbit, we have lighting conditions that are representative of objects in space, and so allows us to launch tools and modules into orbit, put them on the space station, and then use those robotic technologies and all the infrastructure that comes with the space station to mature those technologies in a way that's much, much less expensive than if we try to launch our own satellite and demonstrate those for the first time, not using the space station.
For these endeavors, Nexus's work with astronaut tools, satellite servicing, and on-orbit assembly and manufacturing will do the trick.
We develop the technologies that are needed to advance exploration in ways you can service satellites in the future, build satellites and build structures on orbit, refuel satellites on the way to other planets, repair those satellites much like we do on that side of space station. Both humans and robots are used to maintain habitats in space. We're developing technologies that can be used by NASA and others to make those a reality.
The International Space Station is the perfect testing ground for technologies that will be used to propel humans farther than we've ever gone before. The station is helping us build the necessary foundation to make it possible. Outside of the International Space Station, space can be a lonely place. Most satellites are designed to live their lives alone, and we've yet to find life outside of Earth. This means that when we launch a spacecraft or satellite, for the most part it's on its own, and has a limited lifespan based on when critical items like fuel run out or something breaks. You wouldn't throw away your car if it ran out of gas, and thanks to the advent of modern-day robotics, software, and computing power, we will soon be able to apply that logic to satellites. We are on the cusp of breaking the one-and-done paradigm that exists for most satellites. An important step in that direction is NASA's Robotic Refueling Mission, or RRM, demonstration on the International Space Station. Because refueling a satellite that was not designed to be refueled has never been done before, practice is key. With that in mind, the first two phases of RRM took place on station from 2011 to 2017, and tested the tools, technologies, and techniques to refuel and repair satellites in orbit.
RM and RM Phase 2 were designed to demonstrate end-to-end refueling of a spacecraft, as well as the first steps of cryogenic refueling or replenishment. We wanted to use the robot on the International Space Station to be able to demonstrate the technologies and techniques to do this refueling, so we built innovative tools to bridge the gap between the robot and the payload interfaces.
Consisting of a module or box affixed to the outside of station and robotic tools, the demonstrations use station's Dexter robot to operate tools and test servicing tasks such as cutting and peeling back protective thermal blankets, unscrewing caps, turning valves, transferring fluid, inspection, and intermediary steps leading up to refueling.
Once we were all done, we were able to transfer fuel end-to-end through a spacecraft fill and drain valve that wasn't designed to be robotically refueled.
The RRM demonstration helped test and prove technologies that will make refueling satellites not designed to be refueled possible, something that will be further demonstrated by NASA's On-Orbit Servicing, Assembly, and Manufacturing 1 mission. But it also helped to lay the groundwork for designing future satellites in a way to make them more easily serviceable.
These missions were important because we needed to demonstrate in orbit that this technology was ready. There were a lot of people that felt that at the time of RRM that the technology was so far in the future that they didn't feel what we were talking about was possible. So we needed to demonstrate in orbit this technology so that we could start changing the paradigm and incorporate these technologies into the future spacecraft designs and missions.
RRM Phase 1 and 2 were all about preparing an interface for refueling, which in many ways is half the battle. To robotically refuel a satellite, you need to perform a series of highly dexterous tasks to even access the valve. The next step is to actually perform refueling tasks, which is what the next phase, RRM-3, has been demonstrating on station over a series of operations since 2018. RRM is a critical piece of the sustainable spaceflight puzzle that helps us with the ability to robotically refuel, repair, and maintain satellites in both near and distant orbits, well beyond the reach of where humans can go today. For generations, Mars has beckoned. Now, the red planet is within our reach. But how do we get there? The key is in the details, and in the technology. First and foremost, you need fuel. This is not only true for getting to Mars, but for any form of deep space exploration. Being able to replenish fuel on a long-duration journey means massive amounts aren't needed up front, freeing up space for other important things. Enter Robotic Refueling Mission 3, or RRM-3 for short. This demonstration launched to the International Space Station in December of 2018 and has helped us develop tools and techniques needed to replenish cryogenic fluid in space. Transferring cryogenic fluids has never been done before in space. These super cold fluids can be used as propellants, coolants, or for life support systems. Being able to replenish these fluids that run out, otherwise known as consumables, is an important part of the sustainable exploration roadmap. Not just for Mars, but for NASA's Artemis program, which will land the first woman and the next man on the moon. Since refueling cryogenic fluids in space has never been done before, RRM-3 tested the technologies and techniques needed to make that possible. First, we sent the RRM-3 payload and its 3 main tools to space station, where astronauts assembled the parts.
When I was living aboard the International Space Station in the spring of 2019, I was fortunate enough to take part in the very small part in the Robotic Refueling Mission 3. And my job was to unload the components of the actual RRM-3 from one of our visiting vehicles, and we take it into our Japanese experimental module, the GEM, where we have an airlock. And right inside of the airlock, we unpacked all of the boxes, much like you would a piece of furniture that you had to assemble yourself at home. So unpacked all of the pieces, we did a checkout, we worked with the ground, we got everything assembled, and then we placed it into the Japanese airlock. And from there, we were able to put it outside of the International Space Station. So my involvement in RRM-3 was the physical final assembly of the actual components.
RM-3 was delivered to the space station by a SpaceX Dragon on the company's 16th Commercial Resupply Services mission and installed on the outside of station by the Canadian robot Dexter. Dexter then picked up the tools from the JEM airlock and installed them onto the RM-3 payload. The ground operations team was now ready to begin operating the 3 tools to test how they would work in space. For the first set of operations, conducted in August 2019, Dexter used one of the RM-3 tools to prepare the RM-3 module's interface for transferring cryogenic fuel. The second set of operations was then conducted in October 2020. For these, Dexter used one of the remaining 2 tools to insert an 11-foot-long hose in an open port and the other snake-like camera inspection tool simultaneously to verify the hose's position in the inside of RM-3's tubing. This marked the first time that Dexter had tools in both arms working the same tasks simultaneously. The RM-3 demonstration added experience and information to NASA's knowledge base on the storage and transferring cryogenic fluids in space. It is currently still on station, where it will conduct one final set of operations in mid-2022. For getting to the Moon, Mars, and beyond, cryogenic fluids will be used as propellants and to maintain life support systems for astronauts. The Mars atmosphere is made up of carbon dioxide, which could be converted to liquid oxygen, a type of cryogenic fluid that can be used both as propellant and for breathing. Astronauts may be able to fuel rockets or replenish their oxygen supplies using compounds found in the Martian atmosphere. A tool on the Mars Perseverance rover called Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, is set to demonstrate the first ever conversion of Martian carbon dioxide to oxygen, which is another important piece of the puzzle. In order to make a sustained human presence in space a reality, humans and robots will have to work together using technologies like those developed by RM-3 and MOXIE.
A lot of people ask about, whose job is exploring outer space? Is it robots or is it humans? And I believe that it requires teamwork between robots and humans, and that our exploration is not complete or even possible without both. So robots can go farther, they're less expensive, and they can go for longer periods of time. They don't require as much maintenance. You don't have to feed and care for a robot, much like you do if you send me back to space. So like the Mars rovers, the Galileo that explored Jupiter and its moons, the Hubble and the soon-to-be James Webb Space Telescope, they are doing missions in locations that humans to this point don't have the capability to go. There's also something very important about humans wanting to know what it's like to be there. It's not enough for humans to take a picture of Mount Everest or Antarctica and say, oh, okay, that's what it looks like. The human condition is we are born to explore. We're born to say, what if? What's just beyond what we know? And what is it like to be there? And so the human side of space exploration, first of all, it's orders of magnitude closer to Earth. We have not been able to send humans nearly as far as we've been able to send robotic probes. But they're 2 very different missions, and they serve a different type of curiosity.
Mars and deep space are calling human explorers, and RM-3 is a step toward helping NASA answer that call. Though it sounds complex, the idea is simple. Having the ability to refuel will allow NASA to embark on longer journeys to explore the depths of our solar system. Did you know there's a 3-eyed raven currently perched on the International Space Station? Not an actual bird, but rather a technology payload that is helping NASA develop a relative navigation system, or autopilot, for spacecraft. Launched to station in 2017 aboard a SpaceX Dragon on the company's 10th Commercial Resupply Services mission for NASA, and installed on the outside of ISS by station's Dexter robot, Raven is equipped with 3 distinct camera vision systems: visible, infrared, and LiDAR. Combined with NASA-developed software algorithms, this rotating module of technology keeps a weather eye on arriving spacecraft. Raven's head, containing its 3 eyes, or cameras, is always on the swivel, which is made possible by its integral gimbal.
Raven is an on-orbit test bed that was built to mature technologies related to relative navigation sensors and algorithms. Raven was launched to the International Space Station aboard a SpaceX Dragon capsule in February 2017. And it's been operational on the space station since that time. So using 3 different sensors on Raven that are on a movable gimbal platform, Raven can track the incoming visiting vehicle to station all the way from very, very far away, all the way up to where they dock with the space station. So basically, at any given time, Raven can tell you where the incoming visiting vehicle is in space relative to the space station and what attitude or pointing direction it is.
Raven sends the data it collects from tracking and observing incoming spacecraft to its processor or brain, called SpaceCube. This information then tells Raven how it needs to move to continue to track the spacecraft and gauge relative distance and positioning. NASA engineers have taken what they've learned from multiple Raven observations over the years to adjust and fine-tune the relative navigation system as needed, so it's ready for the upcoming on-orbit servicing, assembly, and manufacturing 1 mission, which will robotically refuel a satellite, among other things.
Raven is a sensor system that can image an object, process those images on board in real time with advanced algorithms, and calculate the pose of the object relative to itself.
These factors come together to create something like spacecraft autopilot. Much like a self-driving car can maintain cruise control based on the speed of the vehicle it follows, 2 free-flying spacecraft will be able to dock with one another using this technology. Though this operation is similar to the autonomous docking of visiting spacecraft to station, Raven's unique application is necessary for docking 2 satellites with the challenges of each moving and rotating in every direction during the rendezvous and docking phase.
Using that information to then guide the first spacecraft to autonomously rendezvous with and dock with the second spacecraft. So that means finding it in space, aligning with it appropriately, and then bringing the 2 vehicles together without smashing them into and destroying each of them, all without human intervention.
This capability is the kind of thing you need for docking with spacecraft that were not originally designed to be docked with and serviced, which happens to be a vast majority of them. That's why Raven's time on station is critical for the future of on-orbit servicing, assembly, and manufacturing, or OSAM. The OSAM-1 mission will use Raven's relative navigation capability to autonomously, meaning no humans involved, rendezvous and dock with the satellite, and then telerobotically refuel it. This will be the first time in history a spacecraft not originally designed to be serviced will be refueled as a means to extend its operational life. Raven is also important for future exploration missions.
Raven's technologies can be applied to future NASA missions because if humans want to make a footprint in the solar system beyond low Earth orbit, which is where the International Space Station is located, we're going to have to rely on some form of autonomous docking technologies in the future. Whether it be an unmanned cargo vehicle meeting up in orbit around the moon, refueling tankers located in geosynchronous Earth orbit, or a return vehicle arriving on Mars in advance of a crewed landing, all of these feats will require the technology we're developing with Raven.
Using its 3 eyes, Raven is looking to the moon, Mars, and beyond.
Relying on highly robust autonomous systems becomes more crucial the further you move away from Earth as the communications time increases drastically. Once you move past low Earth orbit, it becomes very impossible for humans on Earth to do these highly complex maneuvers in real time. It's more efficient to allow computers to perform these sequences autonomously without human intervention.
Although Raven has successfully concluded its main mission objectives, it remains on station. Meanwhile, its team on the ground is using what they've learned to develop more never-before-seen technologies that will enable future space exploration.
Before I started digging in that other bag, here you go. No problem.
If you need to fix something in space that wasn't designed to be fixed, it's going to take all the experience you can get. With that in mind, when the International Space Station's Alpha Magnetic Spectrometer, or AMS, needed repairs, NASA's Johnson Space Center and Goddard Space Flight Center used their joint expertise to make it happen. At Goddard, that expertise resides in NASA's Exploration and In-Space Services Division, or NEXUS, which evolved from the office that was responsible for the Hubble Space Telescope servicing missions. Key to these missions was the development of specialized tools. While you've probably heard of Hubble, you may not be as familiar with AMS, so let's start there. Designed for a 3-year mission of sifting through cosmic ray particles, AMS has been looking for signs of dark matter from its position on station since 2011. Hundreds of researchers have used the data collected to investigate the source of the mysterious substance to help us better understand the origins of the universe. To continue this important data collection, AMS needed an upgrade due to general wear and tear from the harsh environment of space, specifically a new cooling system. A repair could extend its life beyond what was originally planned. Sounds easy enough, right? In fact, due to the instrument's complexity and the fact that it was not designed to be repaired, even gaining access to the system to replace it was difficult. AMS's design did not incorporate the kinds of interfaces that make spacewalks easier, or have the ability to be serviced with traditional multi-purpose tools. And so, over the course of 4 years, NASA got to work designing and developing some of the most complex spacewalks since the Hubble servicing missions in the 90s and early 2000s to fix AMS.
The AMS tools themselves were unique. They were built specifically for this task, a task that was never intended to be performed on a spacewalk. And so that required a lot of thinking about how we were going to get inside so that we could access the tubes that we needed to cut into and then install the new thermal control system, but also how to put handling aids on it so that we had a place to attach our tethers, to attach our foot restraints, to have handholds, have a place to attach equipment that we needed out there.
NASA developed 20 specialized tools to make the job possible, and on November 15, 2019, astronauts Andrew Morgan and Luca Parmitano got to work. On this first spacewalk, astronauts needed to get access. By design, 5 of the tools could be seen floating off into space, attached to the debris shield that was removed to give the astronauts access to the heart of AMS.
The debris shield handling aid was one of the first tools that Luca installed on the EVA, and this gave us a handhold to install on the debris shield to work from, but also a handle for me to hold on to ultimately when we jettisoned it overboard to the aft side of the ISS, which was a lot of fun to do.
The astronauts continued with 3 more spacewalks over the next 2 months, using all of the specially designed tools. One such tool was the tube cutting guide, which was a direct result of multiple practice sessions at Johnson Space Center facilities like the Neutral Buoyancy Lab. While practicing, astronauts communicated the need for a way to identify and verify the correct tubes to cut, since they all look the same to the astronauts' eyes within the spacesuit.
After we had removed the debris shield and the VSB cover, now we have the tubes exposed, and we actually had to cut into those tubes in order to pull out the correct ones to connect with the new thermal control system, the new pump. In order to do that, we had to be very sure of the tubes that we were cutting. These ingenious tube cutting guides installed over the top of the tubes and made sure that we knew and we were communicating correctly with the ground team to make sure that we were cutting the correct tube at the right time.
In January 2020, Luca Parmitano and Drew Morgan completed the 4th and final spacewalk to repair AMS. Because of their work and the ingenuity of tool designers and engineers, the instrument is now back in commission and able to continue to collect data about the origins of our universe for years to come.
People from Goddard and JSC spend a lot of time developing these tools with their knowledge and the support of astronauts like Chris Cassidy. And we are very thankful that we were privileged to use those tools and to put them to very successful use. Thank you very much.